Okay, I would like to start a couple of minutes earlier because I would like to explain for all of you the rules of today. Today, as you know, we have a very tight schedule, as I already mentioned in my email. So we need to be very precise on the timing. Therefore, each speaker, this session, we are all invited speaker. So each speaker has 15 minutes plus 5 minutes of questions. So at the 14th minute, I'm going to tell you that you need to wrap up, and then we allow for the 5 minutes. And welcome all to this is the third block of the GRB session that it is entitled as the gamma ray burst correlations, observational challenges, and theoretical interpretation. So the main scope of these sessions, this is the third, is to investigate the correlations among important properties of gamma ray bursts, to highlight the observational challenges that we need to face to arrive to build those correlations, and what it is the theoretical interpretation. Okay, so having said that, I would like to leave the space to the first speaker of the session, Paz Beniamini. So please, Paz, share your screen and tell us about the structure of gamma ray burst beyond GRB 170817.
Thank you very much, Maria. So let me just sort out this presentation here. Okay. So yeah, thanks for having me. I want to talk today about the structure of gamma ray bursts beyond 170817. I'll have to go very quickly. As Maria said, we are very pressed for time here. So as you all know, 170817 was the first confirmed GRB which was detected in coincidence with gravitational waves that enabled us to literally see bursts from a different angle. And in particular, this burst is about 4 orders of magnitude fainter than any cosmological short GRB that we have seen before. The implications of this joint detection and the follow-up with the electromagnetic telescopes all across the electromagnetic band enabled us to pinpoint what was going on here, especially in the afterglow phase. And to make a very long story quite short, the end result is that we think that there is a successful jet that has managed to break through the neutron star merger ejecta, and that this jet was narrow and pointing far from the line of sight to the observer. Now, this is a very nice picture as we look at the afterglow, but going to the prompt emission, the situation is much less certain. And this very faint luminosity that was seen in the prompt emission for this burst can be explained, generally speaking, in 2 types of ways. One has to do with a so-called cocoon. Basically, this means models where you have a lot of energy to the sides of the jet, but such that this outflow is very inefficient in producing gamma rays. Or you could have a very steep structure of the jet going beyond the core, such that there is literally just not enough energy to power the jet when you look at those further angles, and that's why it's so dim compared to cosmological bursts. So in order to investigate this in more detail, what we would like to have is, from first principles, an understanding of what the jet looks like as a function of angle, both in terms of energy and in terms of Lorentz factor. However, this is a very difficult problem. People try to simulate it numerically, but to do this in 3D and taking into account the full GRMHD is a very complicated problem that is far from being solved at the present stage. And therefore, there is no consensus about what these structures should be. So what I would like to suggest is that there are some other ways that we can get probes about the structure of jets and about how the efficiency changes with angle by looking at data that already exists for long and short GRBs. And I will focus in this part of the talk on long GRBs simply because the data there is more complete and we just have a lot more information for those bursts. So I will very quickly go through 3 arguments that constrain the angular structure, and I will then try to put this together in some way. So the first one has to do with this observed correlation that has been noticed already 20 years ago between the X-ray seen in the early afterglows of the GRBs and the gamma ray energy seen during the prompt emission. This correlation has some scatter to it, but the scatter is not extremely large. It's of order half an order of magnitude or so. The reason that this is important is the following. If you think about the prompt emission, so for typical structures, unless the structure is extremely steep in terms of its energy, what we expect to see is that the emitted energy in any given line of sight is more or less proportional to the observed energy in any line of sight, meaning the contributions from off-axis to the line of sight, contributions for more energetic material that is further away from the line of sight, are typically too dim to contribute much. And you can see this here by comparing the solid lines, which are the available energy along the line of sight, with the dashed lines. Sorry, the solid lines are the observed energy along the line of sight, and the dashed lines are the available energy along the line of sight. And you see that if you restrict the emission up to such angles where the gamma rays are detectable, the two are very strongly correlated. The reason that this is important is the following. If you look at the afterglow, especially when you look far off axis from the GRB jet, at early times, you will most definitely be before the deceleration time, and the luminosity in that regime scales very strongly on the Lorentz factor, approximately as the Lorentz factor to the 8th power. What this means is that if you take the ratio of the two, and you take any reasonable structure for the energy and the Lorentz factor, you expect to have very large variations in this ratio as you start seeing jets beyond the core. So if we had seen many jets beyond the core, and if that was the structure and there was no efficiency cutoff, we should have seen them, they would have still been detectable. You see that we will very quickly overproduce the scatter as compared to observations. One can formalize this in a slightly more fancy way and put restrictions on the slope of the energy profile and the slope of the Lorentz factor profile, these alpha and beta that you see here. Basically, what is needed is a steep structure in energy and shallow in Lorentz factor. There's an independent constraint that can be obtained here coming from the luminosity function of GRBs. Essentially, if you have a structure that is too shallow, you will tend to overproduce the low energy tail of the luminosity function compared with constraints we have from observations. So such models are also ruled out. Putting those things together in this parameter space, you see that we are pushed again to these steep energy profiles with shallow Lorentz factor profiles. However, even those profiles don't actually work out. So let's take, for example, alpha of 5 and beta of 0, very nicely here in the allowed region. What you get for such a burst, even if you restrict yourself to such angles where the gamma rays are still detectable, is that the afterglows will look very shallow for very extended periods of time, lasting tens of days or more, and in fact shallower than any single one of the bursts that have been detected with Swift over the years. And it's worthwhile keeping in mind that these afterglows should not only be there. If this was the true underlying model, they should have been the most common ones, simply because there is so much solid angle associated with these bursts. So what is the solution? We had some parameter space, we ruled out some of it, and the rest also seems to be ruled out. So what I would like to suggest is that all of these three considerations can become self-consistent if we add one more ingredient here, which is that the efficiency of producing gamma rays has to decrease significantly once we go to great angles. And as it turns out, if the efficiency drops significantly at an angle that is about 50% greater than the core opening angle, or equivalently, if the Lorentz factor of material that can efficiently produce gamma rays is at least 50, then we regain consistency with all of these observations. One specific model that does this is shock breakout from a cocoon. This is a model where you have a very efficient emission when you look at the jet core, but once you go to the sides of the core, you have this very inefficient mechanism of producing gamma rays through shock breakout. How can we tell for short GRBs if this is really what's going on? Remember, this data that we have is for long GRBs. Well, the best way to do it would be to wait until we have gravitational wave detections, jointly gravitational wave detections with gamma ray detections would be the ideal case. And by simply the number of such cases, and also by looking at the properties in terms of luminosity and observation angles of those joint detections, we will be able to quite quickly say which of those two underlying models is really the true one for the jet structure. So this is somewhat in the future. So you may justifiably want to have something right now in our hands. And what I would like to suggest is that we can look at another interesting observed phenomena in GRBs, and that may already give us some clues as to the jet structure. And this phenomena is X-ray plateaus. So you're all very well familiar with X-ray plateaus. These are seen in a large percentage of bursts, periods where the X-ray light curves is approximately flat or relatively shallow before it decays back to what we call the normal decay slope of about t to the minus 1. And what I would like to suggest is that for the exact same reason that if you look at very large viewing angles, as I've shown you before, you get these very extended periods of shallow emission. If you only restrict your viewing angle now to 50% beyond the core, which, as we said, is what we think is the consistent interpretation of all the other pieces of information that we have, then you will still have these plateaus, but now they will last a much shorter time scale, between tens of seconds and 100,000 seconds, which indeed matches with what we see for the plateaus. Another nice feature is that if you change the viewing angle only by a small amount, you will get here that the duration of the plateau changes significantly. And basically the physics is that the core of the jet is initially off axis, but over time it gradually comes into view as the core is decelerating and the beaming from the core becomes less and less significant. You can also see here that these light curves have some curvature to them. And indeed, when you look at observed light curves, you see that this is a pretty standard feature. We see this quite a lot in plateaus. Actually, plateaus are not really always flat. There are many cases where we see this curvature. This model also nicely reproduces a lot of the observed correlations between plateau properties and gamma ray properties. It is very easy to understand why those two properties would be correlated in this model. Essentially, the energy that we see in the plateau is correlated with the energy along with the line of sight, which in turn is correlated with the energy of the core. And that also dictates the energy that we see in the gamma rays. So it's very natural to have this correlation, which is not the case, for example, in models where we have energy injection. This model also reproduces nicely the fraction of bursts that have plateaus, as well as spectral features that are seen during the plateau. Finally, as a bonus, it seems that the same model that explains plateaus as being very slightly off-axis GRBs can also explain another mysterious phenomena that is seen in X-rays, which is X-ray flares. So X-ray flares, again, you're all very familiar with them. These are these very rapid spikes in X-rays that are seen in many bursts. And the idea here is that if you're looking slightly off axis, you could have a situation where what would have appeared as a gamma ray pulse, were you to observe it on axis along the core of the jet, will now be slightly Doppler deboosted, such that it will appear at a later time, at a lower frequency and with lower overall energy, and could very well mimic an X-ray flare. So we are working on the details of this specific model, but we find this to be quite promising. And it seems that we may be able to get an explanation simultaneously for both these two things, which would be quite interesting if this is the case, and would also tell us something about the structure of the GRB jet close to the core of the jet. Finally, I want to talk a bit about the future. So looking towards the future, when we think of GRBs that will be detected in gravitational waves, one of the most common electromagnetic counterparts for such GRBs will be in the afterglows. So afterglows are much more likely to be observed in coincidence with gravitational waves than the prompt GRB. And therefore, it is worthwhile to try and understand as best we can what do afterglows from structured jets look like when we see them off axis. And here you see an example of a flux map. And the flux map here is centered on the observer, and the jet is this, the core of the jet is this white X that you see here to the side. And you see that at early times, the emission is centered around the observer. This is because the core is going too fast and the beaming from the core completely kills the emission from that region. We cannot see it. As time goes by, these flux centroids start diverting further and further to the left until eventually they are centered on the jet core. What this suggests is that we can understand the properties of the light curve if we understand this important variable here, which is how the minimum angle that we can see coming from the core of the jet evolves with time. This theta min, how it evolves with time. And what I want to show you here is that we can write an equation for this analytically, and that it matches extremely well with the full numerical integration over the jet. So using this information, we will be able to construct light curves from a purely analytical consideration in such a way that, as you will see, is independent from a lot of the unknown parameters that are typically involved in GRB modeling. So to make it a bit more intuitive, we can look at this picture here of the gamma profile as a function of theta. And you can see that there are a few characteristic angles here. There's the angle of material that is currently decelerating. We call this theta dec. There's the angle of material that is currently being deboosted towards the observer. This is theta beam. And you see here that, importantly, the order of these two angles is going to switch once we go beyond this critical angle theta star, which is the angle from which right at t equals 0, the emission is deboosted, is not beamed. What it means is a bit more clear if you look at this diagram of theta as a function of time. So if you take an observer here at theta observed A, for such an observer, material is first decelerated along the line of sight and only then becomes deboosted. This means that such an observer will observe the afterglow light curve to first peak before the deceleration, then start declining.
It's time to wrap up.
Okay, I will wrap up in 1 minute. Then start decelerating and go down, much like in a cosmological burst. Then, as this theta beam comes into play, we will start seeing material from smaller and smaller latitudes until we see the jet core, at which point we get a second peak and then a second decline. If we look at a greater viewing angle, right from the earliest moment of observation, we are seeing this decreasing latitude as a function of time, so we will only see a single peak. So this can be summarized in these figures. You see that we get either double peak light curves or single peak light curves, and we can analytically write the equations for the timescales and the slopes and the fluxes. And the important thing is that by looking at the shape of the light curve, meaning those slopes and the ratio of times or the ratio of fluxes, this becomes completely independent of the most notoriously degenerate parameters in GRB fitting that you see here, and it only depends on properties of the jet structure, the viewing angle, the slopes of the Lorentz factor and energy profile, and the compactness of the core. And this is just to show that this can already be used to understand the GRB17 or 817 and constrain some of the parameters for that burst. So I will just leave you with my conclusions here and take any questions.
Okay, thank you very much, Paz, for your very interesting talk. So are there any questions or comments for Paz? Okay, I don't see any, so I will start asking. You mentioned that in the modeling for modeling the plateau emission, you could reproduce some of the observed correlations. So and one, it is the luminosity at the end of the plateau emission versus time and of the plateau emission. Can you tell us a little bit more what it is the typical distribution of the parameters that you would get fulfilling this this correlation within your model?
You can see here that the black points are the data, the curves are coming from our model. So essentially the specific distribution along those curves depends on how many bursts we view from different viewing angles, which is something that depends on the exact structure just outside of the core and on this efficiency and how quickly it drops as a function of angle. But in principle, if we know the structure, we can calculate it. And what we find is that we need very steep structures for the energy to get something that looks similar to these observations. So the structure needs to fall quicker than theta to the -6 in terms of energy.
Okay, and in terms of the theta, what would be the angle?
The Lorentz factor?
Lorentz factor and the jet opening angle, what it is the characteristic that you would get as an average? Or I don't know if you get like a Gaussian distribution or
the Lorentz factor as a function of theta is also has to be rather steep, but this is somewhat degenerate with the efficiency. So if you say that the efficiency cuts off beyond a certain Lorentz factor, say below a Lorentz factor of 50, then you can't really probe the Lorentz factor distribution below that. So all we can say is that these two are degenerate. If you have an idea for one, we can constrain the other. For the typical values, these are the same as typical values. We used values that are standard, like theta naught of 0.1, energy taken from the luminosity function of long GRBs, and so on.
Okay, I see. Thank you very much. I think there is a question by Don. Don, please go ahead.
Yeah, when you say the efficiency drops at a Lorentz factor of 50, did you have a physical mechanism in mind, or was this more like, well, if we do this, it works?
Yeah, so first, that's what we found based on this study that I told you about before, which is to do with this different constraints coming from X-ray afterglows. And actually not all of them from X-ray afterglows, some also from the luminosity function. So it's true that this is what we find that works. What is the reason for that? That's now speculation. There are some models where this happens automatically. For example, this idea of a shock breakout from a cocoon will give you automatically that for low Lorentz factors, you have a very inefficient process of converting energy to gamma rays. What makes the mechanism that operates at higher gamma suddenly stop below gamma of 50? Well, we don't even know what that mechanism is to begin with, right? We don't have a clear understanding of what the prompt emission, what produces the prompt emission. There are different models in play. But just to give you a sort of example for how this could work out, even in a model like internal shocks, this is certainly something that is expected. Because if you have internal shocks, then as you change gamma, as gamma decreases, you may have a transition between a situation from which the internal shocks happen above the photosphere to a situation where the internal shocks happen below the photosphere. This ratio of these two radii goes as gamma to the -5. So changing gamma by a small amount could make you cross that transition, and that could shut off the efficiency very quickly. Because if the internal shocks happen very far below the photosphere, then by the time this emission gets to the photosphere, you've lost a lot of this energy, and you get a much, much weaker burst out of this.
Okay, thanks.
So thank you, Paz, again, and we move to the next speaker of the session, who is Simone Di Chiara. Simone Di Chiara will tell us about evidence of extended emission in high redshift short gamma ray burst.
Hi, thanks. Thanks, Maria. Okay, let me put the presentation on. Can you hear me? Yeah.
Yes, yes.
Thank you. Perfect. So for the one that doesn't know me, okay, my name is Simone Di Chiara. I'm a postdoc in University of Maryland, NASA Goddard, and today I'm going to present this work focused on the study of high redshift short GRBs. Just to introduce very briefly, I mean, GRBs are divided into two main classes. We know based on their duration and spectral hardness. Okay, in this figure, you can see the distribution of the duration expressed in terms of T90. You can see the characteristic bimodal distribution used in order to define the classes. And also the other figure, you can see the hardness ratio versus the duration. You can notice that short gamma ray bursts are typically harder in spectrum. They have an harder spectrum with respect to the long ones. The two classes are associated with different kind of progenitors, while for long duration GRBs, there are several pieces of evidence that they are directly connected with core collapse supernova, with the final phases of the life of very massive stars. Short GRBs, on the other side, are associated with mergers of compact object, binary neutron star, black hole neutron star. Apart from these two main classes, there is another type of hybrid events, let's say, which was discovered by Swift in the past. These events have a first short peak at the beginning of the light curve, and which this first peak have typical features, the typical features observed for the short burst. So it's typically armed in spectrum and it's short in duration. So, but this first peak is followed by a long tail, which can last from several tens up to 100 of seconds. And it is characterized by a soft spectrum, and it resembles to a typical long burst. You can see here in the figure an example. This is probably the most famous example of a short GRB with extended emission is GRB 060614. As you can see, the extended emission is mainly visible in the low energy channel, and it becomes less important passing from the low energy channel to the high energy channel. There are different pieces of evidence that point to a possible common progenitor between short GRB with extended emission and the canonical short GRBs. First of all, here you can see the spectral lag measured for this event is consistent with 0. The black diamonds here are short GRB with extended emission, and the gray diamonds are canonical short GRBs. This is different for long GRBs. The spectral lag for long GRB is higher than 0, and typically it correlates with the luminosity of the gamma ray emission. Other than this, we find that we know that several short GRB with extended emission are identified inside old galaxies, late type galaxies. So galaxies that are similar with the population of observed for canonical short GRBs. And another piece of evidence actually is that short GRB with extended emission are not associated with any supernova emission. For example, the GRB 060614 that we saw before was observed at a redshift of 0.1, and we did not find any evidence of supernova for it. So there are all these indications seems to favor a physical link between short GRB with extended emission and canonical short GRBs. So pointing to a possible binary neutron-star merger as a possible progenitor, although the long duration of the prompt emission poses challenge to our common understanding of the neutron-star mergers. Other possible explanation actually for long GRB with extended emission include the formation of a long-lived, highly magnetized neutron star, so a magnetar basically, or a merger of white dwarf or with a white dwarf component, or even core collapse supernova, so a more progenitor that are more similar to the progenitor of long GRB. For example, in case of subluminous supernova, can explain why the fact that we don't see any supernova associated with them. Or there is also the other possible explanation. It could be related with viewing angle effect, similar to what Paz was describing before, for example. One important thing that we need to keep in mind when we use the standard criteria in order to classify the burst is that the burst duration is not an unambiguous tool that can be used in order to define the nature of the burst and the possible progenitor. We performed a set of simulation taking as a template the light curve of a typical short GRB with extended emission, and considering considering the swift back response of the detector, different background levels, and different distance of the source. As you can see, the estimated duration, the T90, can vary. The T90 is the pink region here. It can vary significantly, and it changes a lot depending on the GRB distance, first of all, the level of the background, and also we check how it changed for different active detectors, for a different detector sensitivity, let's say. And the extended emission would be easily missed for GRB that occur at high redshift. And the event would be misleadingly classified as a standard normal short GRB. And an example of this is GRB 181123b. This event, for this event, the standard procedure, the automatic analysis measure a T90 of 0.26 seconds. Although the extended emission cannot be clearly recognized from the study of the count rate light curve, even if there is a marginal evidence of an extended emission, even in the light curve, but cannot be clearly recognized, we use a tailored search, so a devoted analysis, in order to look for a possible extended signal in the image, in the detector, analyzing the detector image. And this analysis revealed the presence of an extended emission. Moreover, another piece of evidence is from the X-ray light curve, we can see that there is an excess at early time that cannot be interpreted as forward shock. So I'm showing here the rate. I'm showing here the X-ray, the gamma ray and X-ray light curve of this GRB, together with the extrapolated optical data. As you can see, there is an excess at early time. And it could be interpreted as the tail of the extended emission that is protracted up to X-rays, for example. Motivated by this discovery, we analyzed the signal of the whole sample of short GRBs with redshift higher than 1, so at high redshift. From the total, so we have a total sample of 8 events, and we find evidence of extended emission for 5 of them, which is about 60% of them. This fraction is quite high, and is definitely higher than the fraction of short with extended emission derived from the general population of short GRBs, which is typically 25%. So we find a very high fraction of extended emission for them. And we see here the distribution of redshift for these GRBs at redshift higher than 1, and I indicated in red the ones with detected for which we detect the extended emission. Considering the selection effects that affect the duration measurement that we saw above, and we need to consider a set of different features that can help us to better characterize these events, the events, and to find a more solid way, to classify them. In order to assess the classification of these bursts, we check different indicators. The first thing that we check is the properties of the prompt emission. And so we checked whether these bursts are consistent with the correlations observed in the peak E-ISO plane. So I show here the observed distribution of short and long GRBs in the peak E-ISO plane with the respective correlation. And you can see in red are our the GRBs in our sample of short at high redshift. So the majority of our bursts, with the exception of 1 or 2 cases maximum, are consistent actually with the correlation observed for long GRB, are consistent with the blue part of the plot. And other than these, we studied the host galaxy properties, derived for our sample of bursts. In the figure, you can see the star formation rate compared with the stellar mass of the host galaxies. In blue is a sample of long GRBs with redshift between 1 and 2, so similar range of redshift of our short GRBs. And in red is our sample, and in orange are the host properties derived from short GRBs detected for redshift lower than 0.5. You can see that while the hosts of low redshift short GRBs are pretty different with respect to the ones of long GRBs, the high redshift short GRBs.
Time to wrap up. You have another minute.
Yeah, just 1 minute. Yeah, and the properties of our sample are more consistent with the one of long GRBs. I have to say that here there could be selection effects that are playing a role, because the ones with higher star formation rate, the galaxies with higher star formation rate are easier to detect at high redshift. Well, but this is the conclusion. I mean, the point is that we find a high fraction of short with extended emission at high redshift. So there are different hypotheses that we have to consider. The first one is that these GRBs are actually long GRBs. So they belong to, they have a collapsar progenitor. This is the first hypothesis that we have to consider, for example. The second hypothesis that we consider is that there is a redshift evolution. So this could explain why we see more short with extended emission at high redshift. And the third one is take into account the possibility that there are strong selection effects for which we cannot see short GRB at high redshift, and we see only the one with extended emission. Let's take into account that the short GRB with extended emission are typically brighter than canonical short GRB, so they are more likely to be detected at a high redshift and well localized. As I said, the selection effect can also explain the high star formation rate. So finally, just to conclude, it seems that the last hypothesis, the selection effect hypothesis, is the favorite one, because while the first two hypotheses are in some tension with the measures of binary neutron star of the binary neutron star population and the air process abundances measured in our galaxy, the third hypothesis is in agreement with it. Actually, it can explain the dearth of short GRB expected at high redshift. So it would imply a large population of binary matter in the early universe. So thank you. That I conclude. And if someone is more interested, this is the link to the paper, and you can send me mail to this mail.
Okay, thank you very much, Simone, for your nice presentation. And now it's time for questions or comments. If you want, you can raise your hand. Okay, since I don't see any hands at the moment, I will start with the first comment. So I agree with you, Simone, that most likely what we see is an effect of selection biases. And I would encourage to use the analysis that we did with Petrosian and Bowden this year, to 2021, in which we show clearly that there is a mismatch between a star formation rate and the density rate for short gamma ray burst, and the evolution for short gamma ray burst is even as strong as the long, or in depending on the population, but we have like a factor of 3.2. So if you have any luminosity, you need to divide by 1 plus z to the power of 3.2 or 3.8. I mean, including the error bar. So in your plot of a peak ISO, also this distribution that you have may change according to the selection effects and the redshift evolution, both for long and short GRBs. And in your diagram about the star formation rate, yes, also this may change because if you can practically compute the evolution for the star formation rate, this again can change. So there are several works that have been done in this realm, and you can apply this correction and see if you still see some of this clustering. Also, another question that I have: did you run a Kolmogorov-Smirnov test or t-test?
Sure.
Or
we did
how
that.
much is the KS test for this two distribution?
We find that a p-value of 0.1 for the short to be. I mean, we checked even if the one in our sample can belong to the same population of the blue one, and and we also apply correction, and we checked if they are of the same population of the short. And we find that, the p-test, I mean, the probability, the p-probability is like 0.1, the 2D Kolmogorov test for this red to be the same population of the orange one. So, and instead it was like much more consistent to be, you can see even from the figure, they are practically in the middle of the blue ones. So the Kolmogorov test it favor the hypothesis that they belong to the same population of the blue long GRBs. But, you know, there could be a selection effect. So it's difficult to say, you know.
Yes, there is another question by Irlan. Are there cases, I'm reading from the chat, are there cases when the same burst observed by both Swift and Fermi could be misleadingly classified as short due to sensitivity of the instruments?
Definitely, yes. I mean, of course, if you have two satellites, so observing the events, you have less possibility to get misled, in the sense that if there is a tail, the fact that you don't see it in both, I mean, it can happen. Yeah, it's possible that you can miss the tail or measure a different T90, a misleading T90 from both the light curve. I mean, the one measured by Fermi and the one measured by Swift. But of course, if you have more than one detector that is observing the GRB, it's better in the sense that it's possible. It's less possible that you get misled, you know.
Yes, thank you so much. And I want to add a brief comment. Indeed, the definition of T90 is instrument dependent because it was originally done for the Batze GRBs, but we have a plethora of works in the literature that show that, for example, there is a paper by Bromberg et al. In 2013 that shows that actually you can have a different population if you, for example, use T90 equal to 0.8 seconds for Swift GRBs, and also if you consider, for example, the T90 of Conus wind or Fermi GPM, sometimes you find that some GRBs are really not short in several of the the several instruments. I found myself this problematic when I was compiling this category for this short with extended emission for finding out the evolution. Yes, you were saying about Bromberg. Yes.
Yeah, Bromberg measured the probability of being non-collapsal. I mean, the probability of being non-long. Yeah, and it is different for different. You get different results for different satellites just because of the different sensitivity, the different instruments. Yeah, instrumental effect.
Okay, there is another question. This is really the last one. Why don't you take into account cosmological dilatation for GRB with non-redshift? From Irene Arcangel.
This could be a very good hint to expand of course the sample and do a more statistically significant, to obtain more like a more statistically significant result. We didn't do that just because we just focus on the one with redshift at the beginning, but it's a very good idea. I mean, we could do that, yeah.
Okay, thank you so much, Simone, and let's move on to the next speaker of the session, who is Lucy Strong, and she will tell us about a model for X-ray plateau following short gamma ray burst.
Hi, everyone. I assume you can all hear me okay. So thank you for having me here today. My plan is to use this time to tell you about a model I've built along with my PhD supervisor, Andrew Malatos, to try and explain X-ray plateaus as they're observed following some short gamma ray bursts. So just to make sure we're all on the same page, as we know, short gamma ray bursts are extremely bright transient sources of light, only lasting a couple of seconds in the gamma ray spectrum. However, the X-ray there's often an afterglow at longer wavelengths. I'm particularly interested here in the X-ray afterglow. We focused on X-ray afterglows, the plateaus, which the literature would identify as having three canonical components. There's an initial decay, there's a plateau phase lasting anywhere from 10 to 10 to the 5 seconds, and there is a final decay. Normally, we see a relatively slow final decay, like we can see here in GRB 130603b on the right. However, there are a handful of cases where the cutoff is very abrupt. And there are a lot of models to try and explain these X-ray plateaus, but there's no single consensus. Most of the models either rely on a series of shocks in a fireball type model or use a central engine. And what we have here is a simple central engine model designed to essentially test some of the basic physics that might have to go into such an idea. And it's deliberately quite simple and analytic so that we can simply play with the ideas without getting too bogged down in the details. So in this talk, I'm first going to do a quick overview of the key physics, a brush over the mathematical underpinning, though that's only going to last long enough to make sure we all know what's happening. And then diving into comparing to the data, in particular the light curves, the correlations, and the observed spectrum. So first of all, starting as many people have with these models before, we assume that there's a remnant compact object and that it's a neutron star. This isn't absolutely a given, of course, but it is a possibility, so we're going to use that assumption. If the neutron star is supermassive and only held up by rotational energy, it may collapse after some amount of time t-call, and that's actually quite okay in this model as long as it's alive long enough to fuel the plateau that we observe. You can change the mass and radius as you wish to do your own calculations, but we just use the canonical values of 1.4 solar masses and about 10 kilometers. And we assume that it's going to be born with an initial spin frequency omega naught, corresponding to a period of about 1 millisecond. We assume that the magnetic field surrounding the star is a simple magnetic dipole characterized by the field strength at the poles B naught, and that's going to be greater than about 10 to the 12 gas. This means we're looking, of course, not just at a regular neutron star, but at a millisecond magnetar. As it rotates, it's going to undergo magnetic dipole breaking. And if we assume a pure breaking index n equals 3, then we get the well-known solution for spin-down luminosity, where we have here, there is this L naught, which is essentially the initial spin-down luminosity, and this tau, which is the spin-down timescale. Now, there's two things I do want to mention here. One is that this spin-down timescale tau, when you plot it out, it ends up being roughly the duration of this long flat period here in the spin-down luminosity. The second thing I want to mention is that when you have assumed a specific breaking index of n equals 3, once you've specified your mass and radius, then L naught and tau are completely specified by your magnetic field at the poles B naught and your initial spin frequency omega naught. This is just a neat little trick that we're going to be using later, so I did want to highlight it now. Now, so far, I haven't actually done anything new. All of this has been in the literature for a long time. And when we looked at this, we realized this is actually on the surface very similar to pulsar wind nebulae, the most famous of which is, of course, is the Crab Nebula. In these, they had a central neutron star, and rotational energy was extracted as a Poynting flux. That flux formed a wind, and the wind interacted with the circumburst media to launch a series of shocks. One of those shocks propagates back into the wind and forms a bubble of electrons between shocks, and this bubble of electrons was assumed to be responsible for the observed X-ray radiation. We essentially lean on this to fill in the gap of how we go from that spin-down luminosity into the actual X-rays we observe. And the key differences to the old supernova remnant models are that we have higher energy scales a more rapid shock, and much stronger magnetic fields. So into the details of our specific model again, there is an external shock, which we model by the Blandford-McKee self-similar solution for a spherical relativistic shock. We assume this is launched when the short gamma ray burst detonates. We make it spherical, not because we actually believe it's going to be spherical, but because they're observed as point sources. And since this is a first pass at an analytic model for this, making this assumption seems reasonable. Once again, the rotational energy of the star is getting extracted, and that's going to form a wind which will interact with the tail of the external shock. And skimming over the complicated shock dynamics in there, we again get essentially a bubble of relativistic electrons forming behind the reverse shock with a distribution n of E of t. Now, this is obviously not angular, has no angular dependence. And if you assume that everything is uniform in the bubble and that it's expanding at a constant velocity, we also end up with no real radial dependence. It all gets wrapped up in the time dependence, which means it's actually possible to model this entire system with a spherically symmetric time-dependent partial differential equation. To do that, we need two components. First of all, there is the electron injection, which we just assume is a standard power law between some upper and lower bounds, E plus minus naught with an index A. And we assume that the time dependence of that is simply the spin down luminosity we saw earlier. This means that our entire injection term is just the spin down luminosity times the power law times some normalization factors. We also have to think about the electron cooling. Now, I will mention, yes, there is adiabatic expansion. In this case, it simplifies down to just E and T, which is lovely, and that's the less interesting form of cooling. What we really care about is the synchrotron cooling, because this is what's going to be producing the X-rays we observe. It's proportional to B squared E squared. And because we have this magnetic field dependence here, we can actually split our model at this point into two variations we looked at. In model A, we assumed that the magnetic field in this bubble is an extension of the stellar dipole field. And this is perhaps the most obvious thing to try and do. We also looked at model B, where we said there is too much that we've brushed over here. We don't know what the magnetic field in this bubble is going to be. So let's just say it's an arbitrary constant B. In this case, there's an extra parameter to deal with, but because it's not time dependent, some of the maths is a little bit easier. And you can wrap that all up into this relatively benign looking partial differential equation where our electron distribution function is changing according to how quickly it's cooling plus how quickly we're injecting electrons. And you can solve this for both models, which is all well and good. But at the end of the day, what we care about isn't so much this n of E of t, even though that's the physical object driving everything, but we care about what observables does this connect to. So just by using standard synchrotron radiation, from here we can start looking at what do we get in terms of basic light curves, how do those behave, what are the spectra we get, and what can we do with these things. All of the data in this part of the talk are taken from the online repository of gamma ray burst observations by the Niels Gerald Swift Observatory website. So first of all, let's start with GRB 130603b, where I've used the known redshift of this particular gamma ray burst to take it to the appropriate distance. And without doing a statistical fit, simply naively putting in some reasonable parameters for that magnetic field strength and that initial spin frequency, I want to see, can I get something that looks kind of like this curve? And the answer turns out to be yes. And at this point, this is actually as far as we have any right to expect this model to get, because as I keep emphasizing, and I'm sure some of you are thinking, this is a very simplified model. But we've been able to reproduce this, so let's see how much further we can push it. The next most obvious thing to look at are the correlations in the light curve plateau luminosity and duration. So here we have a plot where on the vertical axis, we have the X-ray luminosity at the end of the plateau. And on the horizontal axis, we have the plateau duration. Now, I've borrowed some correlation values from Bernardini 2017 and used those to highlight this dark blue region going through the center. This is the observed spread of the relation between the observed plateau luminosity and duration. And then in light blue around that, I've plotted the predicted range for this model. Now, when I say predicted range for this model, I'm talking about the most extreme range I can push out of this. The way I got this range was simply by the upper bound is defined by a spin frequency corresponding to the centrifugal breakup frequency, and then simply letting my magnetic field vary across the full range of parameters it could take. Similarly, the lower bound on this is defined by the most extreme magnetic field I could choose and letting my spin frequency vary across the full range it could take. So in some ways, it's not surprising that this covers a far broader range than is strictly observed in the data. What I think is interesting is that we are able to get roughly in the ballpark. And if we maybe trimmed that parameter space a bit to something more realistic, then we could probably get a lot closer to reproducing what is observed literally in the data. The last thing I want to discuss is how we can use this model and some of the observations to try and infer some properties about that central engine. Now, in an ideal world, we do this by looking at the light curve, calculating the light curve, and doing a fit there. However, for a variety of technical reasons, there are a few challenges to doing that. But calculating the spectrum was very easy and very computationally cheap. So we found 6 short gamma ray bursts of known redshift, and we used the spectra there to try and infer the magnetic field at the poles, B0, that initial spin frequency, omega0, the injection energy range and index. And in the case of model B, that's the one where we had a constant magnetic field. We also needed to infer that as well. We chose very broad priors that were uniform across the L0 and tau, which are of course those spin down luminosity parameters we defined earlier. And when we do that, we started to get results like this one here for model A, which is the one with the dipole magnetic field, and GRB 190627A. So on the left, the first thing to notice is that we are able to reproduce the data. The black points are the observations, the blue lines are draws from our posterior. So we've passed the most basic test we could do for any kind of parameter estimation. On the right, we have a corner plot showing the results for this inference. And there's 2 main things I want to point out here. First of all, there's the fact that despite we chose a very broad prior range, we've managed to obtain parameters that are in fact millisecond magnetar parameters. That's a magnetic field greater than about 10 to the 14 Gauss, peaking at a little bit over 10 to the 15 Gauss. When we look at that initial spin frequency, the upper bound there is the centrifugal breakup frequency. So we are absolutely talking about something with a millisecond spin period. The other thing, and the thing I think will be of particular interest here, is when we look at this plot showing the correlation between omega0 and B0, we get this lovely U shape forming in the data. Now, part of this is just coming purely from the relation between the Plateau luminosity and these 2 parameters, the magnetic field and the spin frequency. But the reason for it being a U is a little bit unclear to me still. And of course, we can do the exact same thing with model B, which is the one with the arbitrary magnetic field. This one is a little bit less exciting. Again, we get the data back, and again, we get parameters consistent with a millisecond magnetar. We get less interesting correlations in the plot here. This is the box that would correspond to the U-shaped plot on the other one. And it turns out for this particular gamma ray burst, when you look at it for this particular version of the model, it is a little less interesting. However, for consistency, I decided to stick with the same one for both plots. In terms of the overall strength of the magnetic field, it's coming out to be a little bit below 1 Gauss. So in terms of where you can find out more about this work, there is one paper about this model that was published in 2019. I've put a link to the archive on the slide. For this stuff, I've spent the last couple of minutes discussing this material about the inference. That's a paper that I actually just resubmitted earlier this morning. So hopefully I will be clear to put it on the archive soon. And if you want to discuss any of this or ask me any questions, if we run out of time, then my email address and Twitter handle are there, and I'm always happy to chat with anyone about any of this. And thank you for your time and for your attention.
Thank you so much, Lucy. And there is already a question by Paz. So please, Paz.
Let's see if I saw this now. So I wanted to mention that if you look at neutron star mergers, if you just look at the masses of binary neutron stars, for example, the ones we know in the galaxy, the typical masses that you expect for the remnant are large enough that the remnant will not be stable against collapse, like you mentioned. And in that situation, what you will get is that there is a certain amount of energy that you lose and a certain amount of time that you can survive before you collapse. If you look at those distributions for the survival time and the extracted energy before you collapse, those are, this distribution of survival time is extremely wide, and it seems to be completely inconsistent with the distribution of plateau durations, where we see this rapid decline at the end of the plateau, which supposedly is connected to the collapse to the black hole. So I wanted to see what you think of that fact. And the second thing is that there is this correlation that you mentioned between the plateau luminosity and plateau duration. Another correlation is a correlation that I mentioned earlier between those two properties and the gamma ray energy. Now, one thing that is not clear to me in this model is why would there be a correlation between the energy in the gamma rays and the energy in the plateau? The energy in the gamma rays is coming from a process that happened early on while the jet was injected. And at that time, most of the energy that will be released by the magnetar has not yet been released. Only a tiny fraction of it has been released. The energy of the plateau comes from the entire energy of the spin down, but it's released on a much longer time scale. So the gamma rays don't know about this energy, and there's no reason that they should be correlated as far as I can see.
Okay, so on the first point, talking about the survival times of supermassive neutron stars, I'll confess I haven't looked at those numbers recently. When we first started working on this model, we actually had hoped to show that with something like this, it wouldn't have an immediate cutoff, but we actually managed to reproduce one similar to what was observed. However, we hadn't looked at those numbers yet and done that comparison, so I can't give a good comment on that. That's something I will have to look into. In terms of the additional correlations, that's not something that we looked into reproducing in this model. As I mentioned, it's very simple. It's skimming over a lot of the details. You could probably do something with, depending on what mechanism you chose for your prompt emission, you could make an argument surrounding what kind of remnant and the energy scales in that remnant you would expect. And you could make an argument that if we think say a neutron star collision producing a short gamma ray burst, when we think about the properties that might make that a brighter and larger burst, it might produce a more extreme remnant. That said, I'm aware that is not a especially strong or thought out argument. That's just my first thought, and it is absolutely something that warrants further thought. To just flip it around, I would say the strength of this is not saying that this is the only way that you could possibly get a plateau, but it is saying that if we do have a remnant that is a neutron star, it should have a relativistic wind like this, and this is one realistic way for it to behave. So we're working from that perspective as opposed to this is the one true solution. I will absolutely read more about those. Thank you.
Thanks a lot, Lucy. I can point you for the first thing. I can point you to a paper that we recently wrote on that, which is Bernardini and Lu.
Yep.
So
right.
I can send it to you.
Okay. Thank you so much. And really, we're running out of time, so we need to move on the next speaker of the session, who is Maria Grazia Bernardini. And Maria Grazia will tell us about the gamma ray burst and magnetars in the multi-messenger era.
Hi, Maria Giovanna. And do you see my screen?
Yes, we can see your screen.
Okay. Okay, cool. So thank you and all the organizers of this session for inviting me to discuss about gamma ray bursts and magnetars. And since we heard a lot about this subject today and also on Wednesday, I will try to give you a slightly different perspective on how we can approach this issue in the multi-messenger era. So first of all, as we heard many times in the last days, actually magnetars that are highly magnetized neutron stars are competing with black holes as source of gamma ray burst power. And regardless if we're talking about short or long gamma ray burst, we in the past years we had a reason to believe that the compact object after either the merger or the collapse of the massive star can be is the source of the GRB power and can be a magnetar, leaving imprints in the GRB light curve. So just to summarize the two kinds of observational imprint that we expect in case of a magnetar central engine, we can divide them in the GRB emission and the kilonova emission associated only to short gamma ray burst, while GRB emission properties are normally common to both long and short gamma ray burst. So in the GRB emission, we heard many times that the first source, the first property, the first feature that led people to believe that the magnetar could be there is the X-ray plateau. So the X-ray plateau is a phase in the afterglow of long and short gamma ray burst with a shallower decay compared to the standard afterglow theory. And since the very beginning, people believed that this shallow decay was related to the energy injection into the afterglow. Apart from that, correlations found between plateau properties and between the plateau properties and the prompt emission properties, as for example this fundamental plane, pointed to a possible relation of this plateau phase with the prompt emission and indeed to the properties of the central engine. And in fact, the main reason that led people to connect plateaus with magnetars is the existence of this luminosity duration correlation, as mentioned many times, and discovered by Maria Giovanna. So, and this correlation is indeed shared by both long, short, and short with extended emission GRBs. So it's a common property of all GRBs showing a plateau, possibly with an offset in normalization. So why magnetar? Because magnetar
I think something happened.
Maria muted herself.
No.
Or someone muted her.
Okay. Okay, we cannot hear Maria Grazia any longer. So
Maria, nobody can hear you right now.
Is there a host who can unmute her?
okay, let me see if I can do some, because it's in Japanese, so I have no clue. Maria Grazia, can you try to speak?
Do you hear me now?
Okay.
Okay, I'm sorry.
Okay, no, so sorry.
How,
yeah.
but,
okay, yeah, please go on.
Sorry, I don't know how I was muted. Anyway, I don't know as when you lost me. Anyway, I'm not saying. I was saying that the magnetar spin down power provides a straightforward explanation for the feature in the plateau, not only qualitatively but also quantitatively. And indeed, we can get direct estimates from of the magnetic field and the spin period from the fit with different models. We heard a few minutes ago an interesting possibility, but there are even simpler using the simple dipole spin down power formula that gives rough estimates of the magnetic field and spin period of 1 millisecond, of 10 to the 15 Gauss and 1 milliseconds. So these are possible distribution drawn from samples, obtained from samples drawn from the Swift sample or GRBs observed. And as you can see, we are always around these values. But more interestingly, the luminosity duration correlation is implied by the model. We heard also by Buzz that there are other possibilities to get this correlation, but with magnetars, this is quite straightforward. And this related exactly to the values of BNP distribution that we find from the data. And also the scatter is implied by the model by the fact that the spin value can range in a certain interval around a few milliseconds. So there are other features in the light curve of gamma ray burst that led people to connect gamma ray burst central engine with magnetars. I just briefly mentioned the extended emission that was already presented by Simone, so I'm not going into details, but also for the extended emission, among other possibilities, magnetars can, in different ways, reproduce the observed features. And here there are two examples proposed by Metzger in 2008 and Gompers in 2014. Again, other features of the prompt emission can lead to people to believe that magnetars are playing a role, for example, the existence of precursor and postcursor, if we assume that prompt emission is powered by an initial phase of accretion into the magnetar with typical parameters that we expect, and assuming a propeller phase, we can see that both precursor and postcursors or flare are nicely reproduced in a simple way by the magnetar central engine. So these are the observational imprints that we expect from the magnetar into the GRB emission, but there are also imprints that can be left in the kilonova emission associated to short gamma ray burst. I don't have time to discuss details about what a kilonova is, but after me there is a talk dedicated to that. So just to briefly mention that magnetar can provide also an additional source of heating in the kilonova emission associated to short gamma ray burst. And in fact, there is one single case identified up to now. It's the kilonova associated to GRB 200522A, where a magnetar boosting is claimed in order to account for the observed optical emission. And imprints of the magnetar has been found also in 3 other short gamma ray bursts and also in their associated kilonova by a combination of a boosting of the kilonova energy and plateau phases in the short gamma ray burst. Also in the very famous case of 130603b, that is the first claimed case of kilonova associated to a short gamma ray burst, it has been proposed that a possible contribution from a millisecond magnetar is identified in the late time X-ray emission. Although this is connected to the short GRB and not to the kilonova itself. So now a question very simple and partially raised by Pads a few minutes ago is, can magnetars then power all gamma ray bursts? So we have no problem. And we proposed very recently in a work led by Barbara Patricielli a different approach than searching the features of magnetars into gamma ray burst in order to answer to this question. So we did the opposite. We used the catalog of binary mergers, binary neutron star merger, combining in the binary merger rate, the mass distribution inferred from the galactic neutron stars. And we try to predict for different equation of states the number of this merger that ends with a stable or unstable neutron star. So supermassive, stable, or could direct collapse to a black hole, or hypermassive, so a neutron star that collapse to a black hole in a few milliseconds. And we compare the outcomes with the observed rate of short gamma ray burst. In this plot, there are the red and yellow lines for different theoretical assumptions behind. And as you can see, the stars represent for different equation of states the stable or supermassive neutron star, while the black points are the black holes or hypermassive. For most equation of states, the rate of magnetar produced is sufficient to power all the short gamma ray bursts. This does not take into account any estimate for the duration of the supermassive phase. So it's just that a supermassive neutron star can be formed. So in principle, we also have sufficient neutron star magnetars to power at least all short gamma ray bursts, but of course we have also a number of other limitations. First of all, magnetars have a limited energy budget, so a few 10 to the 52 Hertz is their rotational energy, and this, in the case of long gamma ray burst, is often not enough. And even if we know that the true energy is less than the isotropic one due to collimation, even if the study of long GRBs associated supernovae demonstrates that this budget is sufficient to power both these events. Several long gamma ray bursts are too energetic. So probably the magnetars cannot power all long gamma ray bursts. At the same time, for short gamma ray bursts, this energy budget seems to be too much. And in fact, recent work by Ricci and collaborators showed where they found radio upper limits in short gamma ray burst afterglows rule out very energetic merger ejecta. So they exclude, in most cases, powerful magnetar as central engine, since the energy deposited at some times should be observable. The second and most tricky issue is that it's difficult for magnetar to launch ultra-relativistic jets. And this is something that is not settled up to now. And also in a work by Rea in 2016, they show that magnetars powering gamma ray burst seems to be inconsistent with galactic magnetar population. So if we want to believe that these magnetars exist, we have to assume that a population of supermagnetars should be connected with GRBs in a similar way with what happens with type 1c hypernovae connected to long gamma ray burst. So what can we do in order to solve this problem of the GRB central engine in the multi-messenger era? First of all, we have the perfect benchmark in the only up to now case of short gamma ray burst associated to gravitational wave emission. That is GRB 170817A. So what did we learn in this single case? The merger remnant is quite massive, can be either an hypermassive neutron star or a black hole. So we don't have any clue directly from the merger remnant. However, from the electromagnetic observation of the non-thermal emission of this object, we see that the X-ray flux is too low for a long-lived neutron star. And even if there are caveats, this tends to rule out the presence of a long-lived magnetars behind this event. Similarly, the kilonova afterglow that Paolo will present in the next talk, so I'm not going too much in details about that, but also in this case, a magnetar can be advocated, but with a very, very low unusual magnetic field that is 10 to the 9 Gauss, that is inconsistent with what we observe usually for gamma ray burst. So also from the thermal emission.
So it's time to wrap up. You have 1 minute more.
Okay, I'm going a bit faster then. So the thermal emission, the emission of the kilonova, again, argue in favor of a hypermassive neutron star collapsed to a black hole in a few seconds. So even if we don't have the final proof of the nature of the GRB central engine in this case, the rapid collapse to a black hole is the most probable scenario. So this is not the end of the story, because this is just one single case. And indeed, the best way to probe the central engine is to detect directly the gravitational wave from the magnetar. There are different predictions of long-lasting post-merger signals that can be a distinctive feature of surviving neutron star, and also secular instabilities can produce gravitational wave losses over much longer time scales that are comparable to the duration of the Plateau phase, as in these predictions by Christian Mezzaros 2009. So if we detect directly this kind of signal, we can say, oh, well, we're happy. There is a long-lived neutron star that is playing a role simultaneously to the short gamma ray burst. This kind of search has been performed again for GRB 170817A, but unfortunately, these kind of searches are not conclusive, both for short duration, about 1 second, and intermediate duration, 500 seconds signal. But this is not surprising, again, because the expected signals are at least 1 order of magnitudes below the current sensitivities of the of the LIGO interferometers. So the non-detection cannot rule out the presence of a long-lived magnetar for the moment. So the direct detection of magnetar GW signals is hard to get anytime soon, even with the improved sensitivities interferometers, but there are good prospects with the third generation of detectors as the Einstein telescope, because in this case, we go more than 1 order of magnitude below the current expected sensitivities for the advanced LIGO and Virgo. And one of the possible breakthrough with this new new generation of detector is exactly the possible detection of of the signal from the remnant after the merge. So I will go very fast on the conclusion. As I said, the observational gamma ray emission, in particular the X-ray emission, pointed towards magnetar as plausible candidate for central engine. Of course, they are not the only possible explanation, but it's one possibility that put different features together. Are all gamma ray bursts powered by magnetars? Likely not. And in fact, in GRB 1708-17A, we probably are seeing a gamma ray burst powered by a black hole. However, a direct proof, this cannot exclude that in all cases, magnetars are not responsible for the emission of gamma ray bursts, and the only way to solve this problem, or the best way to solve this problem, is to have the direct detection of gravitational wave and electromagnetic simultaneous signal from the remnant of the merger. This will be achievable probably with the third generation detectors. I just leave this slide on, and after my conclusion, just to advertise about this new mission dedicated to GRB science and to transients in general that will be launched in the early 2023. So stay tuned. Thank you very much.
Thank you very much. We have just 1 minute for a quick comment or a quick question. So do you have any? Okay, maybe if not, I would like, there is one.
See Paz has a right hand. Okay.
Okay, yes, sure.
Yeah, very nice talk. You mentioned that there are at least several cases that in the Ricci et al. Study, they showed that the energy cannot be greater than a few times 10 to the 52. This is already kind of pushing towards the energies that we expect these systems to have if they're born at the mass shedding limit. And as you know, if you only need to lose about 20% of that initial energy before you can no longer support this rotation and you collapse very quickly. And so if you then try to have such magnetars where the energy is significantly lower than these values that you have there, the time to collapse will be very short for these cases. So even if they start as magnetars, they won't survive as magnetars for long. So once we are secure that these values of Ricci et al. Really are typical for short GRBs, this doesn't really leave much room for long-lived magnetars. Do you agree with that?
Yeah. Okay, I agree, this is true, and this is something important, although there are other possibilities, for example, mentioned in the literature. For example, Dall'Osso et al. Proposed that there is a possibility that the magnetar emits a lot of rotational energy via gravitational waves and less via electromagnetic power. So there is still the possibility, even in the case of 1708-17A, where there is really a little room for a long-lived magnetar central engine, there are claims that there is a way to rearrange things in order to make the situation compatible with the presence of a magnetar. I personally am not supporting this, but just to say that, of course, there is in different cases room to rearrange things, but I totally agree with you, because especially for short gamma ray burst, as I said, the energy budget is a bit constraining because it's a bit too much in most of the cases. For long gamma ray burst, it's a different story. So
okay, so I want to add also a quick comment out of this that is related to previous comment of Paz. So there is observed a correlation between the prompt peak luminosity with the with the spin period. This is an anti-correlation, and we show this in the paper Stratta dai Notte et al. 2018. So this somehow reconcile the problem of the connection within prompt and afterglow properties. So since this second talk is related to what Lucy Strand was presenting, I think it was nice to close with this comment. Okay, so thank you again, Maria Grazia. Let's move on the next speaker of the session. Paolo D'Avanzo will tell us more about the short gamma ray burst, and in particular the short gamma ray burst situation and future perspectives.
Yes, thank you, Maria Giovanna. Hi, everybody. So I will share. I hope you see my slides in full screen in a second.
Yes, we do.
Okay, and also moving works. Okay, so it's a pleasure to be here. Unfortunately, not in person. Thanks a lot to the organizers for giving me the opportunity to give this talk, during which I will try to provide you a kind of quick overview of the situation we have in the study of short gamma ray bursts and the future perspectives. I will start from presenting the Swift sample of short gamma ray burst. Swift provided as a big game changer in the study of gamma ray burst, because thanks to Swift, we were able to discover their afterglow and those galaxies, and so to measure their redshift. They measure the redshift, and so to measure all the physical rest frame properties of these events. So to date, Swift detects almost 9-10 short gamma ray bursts per year, with a total sample of almost 150 events. About those, some statistics: about 15% show an extended emission. Simone already explained us what the extended emission is, and almost there is a large fraction with an X-ray afterglow detected, but there is not a negligible fraction of X-ray afterglow that were not detected in spite of a prompt slew or Swift with the prompt observation with the X-ray telescope. And then when we move to the sample of short gamma ray bursts with the optical or a radio afterglow detected, the number become a bit lower, and this is of course a problem with the study of this, and putting also to forward selection biases. And in the end, the sample of short gamma ray bursts with the redshift measurement is around 25, maybe 30%, independent of some association. And in the great majority of cases is done with the host galaxy optical spectroscopy. And of course, there are a lot of science cases related to short gamma ray bursts. Many of those have been discussed during this session. And one of the main questions was the quest for their progenitors. So going quickly among the properties of prompt and afterglow emission, we may note that concerning their spectral prompt emission properties, short gamma ray burst as well as long gamma ray burst nicely fit the so-called Ioneau-Tocco relation between the isotropic luminosity and the peak energy of the prompt emission. But if we move to the so-called Amati relation between the isotropic energy and the peak energy, we see there is a well-known correlation for long gamma ray bursts, and it seems that the short gamma ray burst lies on a kind of parallel correlation, as already shown also in previous talks, and also by, for example, by Simone. And what I also always find very useful in this is that this has been used in past recent studies and still used. I find it very useful as a possible discriminant to discriminate between the long and short classes. I'm speaking here about the two different classes of progenitors, because as discussed before, for example, by Simone, a mere classification, a simple classification based on the duration, of course, is not simple or straightforward. Then if we move, I said that we don't have that much afterglow detection because short gamma ray bursts are fainter. Here you can see the rest frame X-ray luminosities here on the left, the short gamma burst afterglow are fainter systematically with respect to long. But the nice thing is that if you normalize everything on the right panel here for the isotropic energy of the GRB, of each GRB, you see that this dispersion disappear basically, and short gamma rebirth, here are the lines, and long gamma rebirth, you see the shaded area here showing the scatter of long gamma rebirth, basically superpose very nicely, so showing a very nice correlation between the isotropic energy and the X-ray luminosity of the afterglow that is especially tight at early times as expected. So it's a good proxy, the X-ray luminosity of the isotropic burst energy. A kind of unified view can come from the three-parameter correlation presented by Bernardini and Margutti, putting together the isotropic gamma ray energy and the peak energy and the isotropic X-ray energy emitted by the X-ray afterglow. And here you can see a kind of unified view for all the gamma ray bursts with two distinguished regions for long and short gamma ray bursts. Okay, so in the context of compact object measure, what do we expect for short gamma ray burst? So we expect a mix of any kind of host galaxy, and this is indeed what has been observed in almost 1.5 decades. So we see short gamma ray bursts occurring in every type of galaxy, and in some tape also there are the so-called hostless short gamma ray bursts, suggesting maybe for high redshift events, or more likely events with a large offset with respect to close by galaxies. We expect into this context a kind of offset with respect to host galaxy that can maybe due to natal kicks and migration of the double compact object from the birth side before coalescence. And while the question for offset maybe can be debated and sometimes can be not that significant, even if there are clear detection from this, for sure, we see that the environment is different for short gamma ray bursts with respect to long, again in agreement with the scenario of the two different progenitors and of the compact binary mergers. We expect no associated supernova, and indeed this is what has been observed in short gamma ray bursts. There is a lot of debate about the kind of remnant that there can be, for example, from a binary neutron star merger, but here already Grazia gave an exhaustive overview, so I will skip this point. Of course, there was the question if a binary neutron star merger or a neutron star black hole merger can indeed power a relativistic jet. And in the past, I'm doing a kind of recap to the situation until 2017. The observation of the so-called jet breaks, so achromatic steepening in the afterglow light curves, has been indeed observed also in short gamma ray bursts, as it was since long time for long gamma ray bursts, so suggesting for a collimated outflow. And of course, there was the expectation for the kilonova in the case of compact binary mergers, and indeed even before 2017 there have been claims in the literature mainly based on the observation of excesses, mainly in the red bands in the afterglow light curves. And of course, the big expected guess were the gravitational waves. And I will now focus on these last 3 points for what changed after the breakthrough on 2017. And of course, as we know, the gravitational waves has been indeed detected from binary neutron star merger event associated to a short gamma ray burst. We all know the story. And follow-up observation of this great event provided the evidence of a kilonova associated that could be studied thanks to the proximity of the event in a very great detail. Here we can see the multicolor light curve and the fantastic spectral sequence obtained through X-shooter that provided the best study we have so far about the kilonova, with a very good match with the prediction of a blue and a red component. In the tail study enabled us to provide this kind of scenario with 3 components, 2 dynamical components, the equatorial red and the polar blue, and a wind component with all these with different ejected mass, with different ejected velocity, and with different composition in terms of the relative contribution of heavy elements. And we all know the story. It was also possible to perform polarimetric study, obtaining deep upper limits in agreement with a kind of symmetric or symmetric shape, of the ejecta, so not just very asymmetric, just equatorial ejecta. And also the spectroscopic study provided some hint of the long sought heavy elements, so everything in agreement. But this peculiar event provided also, as you know, the possibility to study in detail the jet emission, and did all the observations, in particular the final proof arrived from very precise high spatial resolution radio observations, enabled to definitely define that the event originated as a jet with a kind of structure, so different gamma and energy as long as we move through the angle, so a compact core surrounded by a shield, and seen from the point of view from Earth with a theta view of about 20 degrees. And this was also corroborated by the observation at any wavelength of the afterglow that was observed to rise, reaching a peak. Here
Paolo,
you
have
nice.
1 minute, so I suggest wrapping up.
No, but no problem. I'm almost there. So thank you very much for saying this. Nice picture of in the X-rays at the peak with the known thermal spectrum. Is very nicely in agreement with the model of the structural jet. And the nice thing is that we can still observe in the X-rays and in the radio the evolution of this afterglow, and there is the possibility of a kind of flattening of the X-ray light curve, suggesting the possibility of the expected kilonova afterglow, but it is also open to other possibilities like the accretion of the Complex remnant or even magnetar contribution. Although such an interpretation, you see the larger error bars, is now debated because it is possible that just providing different beams in the analysis, whatever, it disappears. So it will be very crucial to wait for new observation to understand. I just point out, as said before, that this is not the first time that a kind of X-ray excess is observed in a shorter afterglow light curve, X-ray light curve at relatively late times. So it will be very nice at some point to have a sample and try to understand in a unified view of this. I see that I just conclude telling you that apart from this very nice event, there are many claimed kilonovae found in archival data of new gamma ray bursts that the claim has been done by the thermal spectrum in the optical near infrared or excesses. So the situation is promising beyond, and that if we have a look and plateau luminosity, time of the plateau, and peak luminosity plane, I find very nice that all short GRB and kilonovae occupy a very defined region in the plane. And this, I think, it will be very nice to be further investigated when new events will be available. A kilonova for every short GRB. There is this is my last slide. This very nice paper by Andrea Rossi and collaborators that provided an overview with a sample load of the short gamma ray bursts with redshift, and found that almost always there is the possibility to associate a kilonova, or the limits are not deep enough to find it, and only in a couple of cases the limit obtained in the optical near infrared of the observation are deep enough to exclude kilonovae like the one of 2017. And I leave you with my conclusion that I think are very promising for the future, even if during the O3 LIGO and Virgo run, we had no good events. But as you can see, the study of short gamma ray bursts and kilonovae can go beyond and can go good expectation for the upcoming O4. Thank you very much.
Thank you, Paolo, for your very nice talk. And are there any questions or comments for Paolo? We have 3 minutes until the next speaker. So I don't see at the moment any hands up, but I have a question. So what it is the expectation for the next LIGO run for the short GRBs kilonova events?
So after the O3, the first O3 catalog of the first part of O3 came out, the rate of binary neutron star merger have been lowered a bit. So the event will be can be less than expected, but still we can have a significant number of events during the 1 year or 1.5 year lasting O4. The main problem will be, and this is what we are discussing now, if reaching a larger volume of universe will be indeed a good thing for people doing follow-up in the electromagnetic, because we can have, of course, much more events, but the problem we faced during O3 is that when you have to look for an electromagnetic counterpart in a very big sky maps of thousands of square degrees is, of course, a problem. And also for the large distance, at that point, galaxy catalogs are not that complete, and this is difficult. My personal opinion is that we will need again to find some hint from the high energy satellite. So a gamma ray burst, subthreshold gamma ray burst in coincidence that can help a lot the observers from the ground to have a look for the electromagnetic counterpart. But of course, usually in such situations, any prediction is typically not attended, because we typically face the unexpected as happened during O2. So I think the only thing is to wait.
Yes, this is very interesting, and I want to add that in the first day of this 3-block session, there was a presentation by Alan Watson for a new follow-up, GRB follow-up that we are performing in conjunction with the KISO Observatory and PI of this follow-up effort. So we hope to see short GRB. The target is for short GRBs, and we aim between the DOTI and the KISO to obtain 16 GRBs per year. So we hope that this can also help, as you said, to bring it up higher, the number of short GRBs observed by telescope ground-based facilities. So thank you so much, Paolo, again, and we need to move on the next speaker of the session. So now, for a change of topic, we will hear more about the diversity in supernovae that are associated with the gamma ray burst. So, and we will, Moria-san is going to tell us about this. Thank you.
Thank you very much, Maria. So I thank you for the invitation, and I'd like to discuss the diversity in supernovae associated with gamma ray bursts. So as you know, supernovae and long gamma ray bursts, I will talk about long gamma ray bursts, and this association was first hinted by the GRB 980425, which was associated with supernova 1998 BW. Of course, I was a child back then, so I have no idea about the field back then. But what I heard is at this time, still maybe half of people believed the GRB and supernovae were associated, and the rest of the half was not so sure. So yeah, at the runtime, it was not that clear. But then in 2003, there was one clear case where this GRB spectra turned into supernova spectra. So I think from 2003, everybody is confident that the long gamma ray bursts are associated with supernovae. So among many different supernova types we have, actually long supernovae which are associated with long gamma ray bursts, so-called broad line type 1c supernovae. So type 1c means there's no hydrogen. So type 2 is with hydrogen, and type 1s are without hydrogen. Type 1b is with hydrogen, without hydrogen, but with helium lights. And type 1c means there's no signature of helium either. So there's basically no helium or hydrogen. And among these type 1c supernovae, there's a class of supernovae called broad line type 1c supernovae, which is also known as hypernovae. That basically they have very extremely broad feature, which is typically interpreted as, well, basically it's coming from high velocity, therefore it can be interpreted as high exposure energy. And now we have many, a lot of samples, GRBs that are associated with supernovae, and also with the modern transient survey, we have many broad line type 1c supernovae and also type 1c supernovae as well. And one thing to note is, so gamma ray bursts are always associated, or if you find supernova component, then they are always broad type 1c supernovae, so with the very broad spectral feature. But broad line type 1c supernovae are not necessarily associated with gamma ray bursts. So we find broad line type 1c supernovae even without GRBs. So we have transient survey, so we sometimes find supernovae which turned out to be just broad line type 1c supernova without any GRB association. So in this figure, these are all supernova light curve, and blue dots type 1c supernova. So type 1c supernova with typical exposure energy or typical velocity. And red dots broad line type 1c supernovae, but without GRB association. Of course, without, let's say, without observed GRB. And this dark red color or brown, they are supernovae associated with gamma ray bursts. So we can see that these supernovae associated with gamma ray bursts has, typically, this at the brightest end of all type 1c supernova classes, and we sometimes have this very extremely bright supernovae associated with GLBs. And usual type 1c supernovae tend to be fainter, but if we see broadline type 1c, it has diversity as well. So what I want to say is that supernovae, associated with gamma ray bursts are quite diverse, and there's no single supernovae associated with gamma ray bursts. This is again so more physical parameters estimated from the light curve and spectral properties. So this is the peak magnitude, and this is the estimated nickel mass. And red dots are all broad line 1c supernovae, and those with open symbols, those connected with gamma ray bursts. So you can see that actually broadline type 1c supernova, which basically means they have high velocities, they can appear with relatively low nickel mass. So consistent with other type 1c supernovae, and some GRB associated supernova also, of course, faint as we saw before. But yeah, many of the supernovae associated with gamma ray bursts are quite bright. This is kinetic energy and ejecta mass distribution. This figure only has some limited supernovae, but so those associated with supernovae associated with GRB tend to have very high explosion energy and also high ejecta mass, while the other broadline 1c, so this broadline 1c supernova without observed gamma ray bursts, or well, some of them, yeah. Without clear GRB association, tend to have relatively less kinetic energy and ejecta masses. So yeah, the interesting question is that we sometimes type 1c broadline is associated with gamma ray burst, and some of broadline 1c supernovae are not associated with gamma ray burst. But of course, one possibility is that GRB has beaming, so we need to be in a good position to observe GRB, and maybe one simple interpretation could be those type 1c supernova, broadline type 1c supernova without GRB may be all associated with GRBs, but we don't simply see the GRB. That's one way to interpret these two differences. But if we see, like, this is the velocity distribution of photospheric velocity distribution of these types of supernovae. This part is kind of summary of average of this observation. What we see is those supernovae associated with gamma ray bursts tend to have higher velocity than those type 1c broadline supernovae without GRB. So it's not it is likely we are not seeing the same phenomenon, but with different angle. So seems there's some differences between type 1c broadline supernovae with and without gamma ray bursts, and those with gamma ray bursts tend to have higher velocities. And this is kind of summary of they have many broadline type 1c supernovae without gamma ray bursts, and they estimated distribution of ejecta mass, kinetic energy, and Nickel mass from type 1c supernovae, broadline type 1c supernovae without gamma ray bursts. And actually, typical broadline type 1c supernovae without gamma ray bursts tend to have ejecta mass of typical ejecta mass is several solar masses, and kinetic energy is also in many cases it's less than 10 to the 51 L, so it's several times 10 to the less than 10 times 10 to the 51 L's, which are often observed for type 1c supernovae associated with GRBs. Of course, there's some population maybe from here, but most of them have a relatively low explosion energy, and so low ejecta mass and low relatively high explosion energy can explain high velocity. Nickel mass also tend to be relatively lower than what we see in supernovae associated with gamma ray bursts. And but the metallicity, if we see the metallicity distribution, actually these two populations, we cannot separate these two populations. So metallicity, progenitor metallicity seems to be similar in type 1c supernova broadline with and without GRB. So the summary up to here is some type 1c supernova type 1c with broadline feature associated with long gamma ray burst, but broadline type 1c supernovae are often discovered without GRBs. And some supernova type 1c broadline likely occur without long GRB. We see general differences in general properties of type 1c broadline with and without GRB. But metallicity seems to be similar. So of course, interesting question is what makes these differences. Yeah, so one way to interpret maybe in both type 1c broadline, in all type 1c broadline, there may be some jet at the beginning, but some jet may be successfully penetrated. In that case, we observe as GRB associated cases, but maybe some case often this jet cannot penetrate the progenitor, and then we only have broadline type 1c supernova. That may be a difference. But then, as we saw, broadline type 1c supernovae without long gamma bursts tend to have smaller ejecta mass than those with long GRBs. So, naive expectation, maybe if the ejecta mass is lower, then it may be easier to penetrate. But of course, if the mass is lower, then maybe you have less accretion and maybe difficult. The central engine may be less powerful, so it's difficult to say. But there seems some such kind of differences in diversity in explosion is existing there. And there's very peculiar cases as well, and this is without supernovae, so this has been discussed. So it may not be even long GRB, as we saw in many talks, but if it were long GRB, one possibility is this may be a fallback supernova, so which means the supernova explosion was not successful, so only most of the material just fall back to the central remnant, and only a small outer layer is ejected as supernovae, and then this supernova component would be extremely bright, faint, and we don't observe it as and the GRB component would be dominant. And actually, such kind of supernovae are known. So this is one example, 2008 HA. This supernova had an ejecta mass of only 1.47, kinetic energy of 10 to the 48, and 10 to the minus 3 solar mass of nickel. So, and the progenitor is actually 13 solar mass progenitor, but most of the material is lost, and only outer edge of the ejector is ejected, and that can make this kind of weird supernovae we actually observe. And another extreme is ultra long GRBs, and this one luminous supernova was known to associated with ultra long gamma ray bursts, 2011 KL, and this is another interesting extreme cases. And what we proposed is this ultra long duration. Of course, this origin is still unclear, but the one possibility is that progenitor may have extended envelope. We found, typical Wolf-Rayet star progenitor has a radius of solar 1 solar masses or around there. But actually, if we think of extremely massive GRB progenitor, for example, 50 solar masses, it goes to pulsational pair instability regime. So before the collapse, it can have surface layer can basically expand because of the pulsation, and this extended structure is kept up to the time of the up to the time of collapse. So this extended structure will just go will be a GRB progenitor. So even Wolf-Rayet star progenitor can have radius of more than 1,000 solar radius. So that may explain the extremely long duration. And if the progenitor has such extended structure, then when the explosion happens, the initial cooling phase become extremely extended, and that may also explain this early supernova bright component. So this may be reflecting extended progenitor, which may explain both ultra long duration and also the this supernova component at the same time. I think I'm running out of time. So yeah, the short summary
yes.
is, sorry. Yeah, supernovae associated with long gamma bursts are very diverse. And yeah, that's it. Thank you very much.
Thank you very much, Moria-san, for your very nice, interesting talks. So are there any comments or questions? Okay, if not, I would like to ask a question. So what is your opinion about the connection between GRB supernovae in terms of correlation? We have started this collaboration on this topic, and what is your opinion
so
in general?
I don't know yet, and you know, just looking at the supernovae, it is really diverse. So I don't see, you know, clear, you know, easy seen, you know, like correlations existing there, but you know, it may tell something about, you know, it may be related to GLB correlations, and you know, it should be, supernova property should be connected to the progenitor properties, and of course the explosion energy and so on will be related to the mechanism powering the GLB. So there should be some connection between GLB properties and supernova properties, which we should see.
Okay, so thank you very much. So for all the audience, stay tuned. Maybe we will have a paper soon with Moria-san on this topic. And I think I would like to leave now the chair to Li-Liang for this next part of the session. And I would like to thank Moria-san again. Thank you.
First, we are very sorry for because today we have two more talks than Wednesday and Thursday. We have to cancel the break. Let's keep going. The lights speak. He will talk about the photospheric origin of the EP, P and EP ESO correlations in gamma ray burst. Oh, welcome. Are you ready?
Sorry, I forgot to unmute myself. So do you see my slide and
yes.
cursor? Okay,
yes.
Good. Okay, let me start the talk. So first of all, I'd like to thank the organizers for giving me an opportunity to talk in this session. So today I'll talk about my study on the photospheric emission of GRBs based on numerical simulations. In our simulations, in our simulations, we find that the correlation between specular peak energy and luminosity and the E-ISO can naturally arise in the framework of photospheric emission. So in this talk, I mainly report on this result. Okay, so let me just start from a brief introduction. I can simply skip this, but as you know, the Monte relation and the Untitled relations are the most popular and established correlations in the properties of prompt emission of GRBs. So while this is often invoked for application to cosmology, it also provides a very powerful diagnostics for the emission mechanisms. So in this talk, I will focus on this aspect. And the question that is tackled in this study is, can photospheric emission reproduce these relations? So to answer this question, we have conducted numerical simulations. So, and before going into details, let me briefly mention on the importance to conduct a simulation in the current study. So since the jet must dig through a massive envelope before the emission, it is quite likely that the photons that is emitted will propagate through a dynamically evolving jet, which has a structure far from a simple top hat-like shape. So in order to assess the impact of the structure on the emission, global dynamics of the jet, as as radiation transfer within the jet must be solved. So in our study, we explore this issue by performing a radiation transfer calculation based on hydrodynamical simulation. And the set of the simulation is as following. So first, we compute the propagation of relativistic jet breaking out of a massive stellar envelope by conducting a hydrodynamical simulation in 3D. Initially, the jet is injected inside the star until and we follow the evolution until it breaks out the star and propagate to large distance up to the point which it becomes optically thin to radiations. Here the considered progenitor star is the we use the widely used Wolf-Rayet star model taken from the previous study. As for the jet parameters, we employ values given like this, which is in the range of typical values used in the literatures. So in this study, we considered 3 models with different jet power shown here, which covers 2 orders of magnitude. Okay, so after solving the hydrodynamical simulation, we solve the radiation transfer calculation using Monte Carlo method. So initially, thermal photons are injected deep below the photosphere, and its evolution is solved. Its propagation through the dynamically evolving jet is solved and up to the point which it is released at the photosphere. So this is how we evaluate the photospheric emissions. Okay, so let me move on to the results of the simulation. Here I'm just showing the 3 snapshots of the 3 models which employ different jet powers, with left being the weak jet model, right being the highest jet power model. So as you can see, when the jet power is weak, it struggles to break out through the star, and therefore global wobbling feature is seen in their structure. But as you increase the jet power, its propagation becomes more ballistic-like due to its higher thrust. So here I'm showing the resulting light curves and spectra for all 3 models. I don't go into detail, but the temporal variation seen in the light curves is reflecting the structure that is developed during the propagation through the progenitor star, and also reflecting the non-uniform structure of the jet. Emitted spectrum shows broadened features broader than the thermal spectrum. In some cases, it becomes compatible with typical observations. And regarding the comparison with the observed correlation between spectral peak energy and luminosities, the most important feature is the viewing angle dependence of the emission. Due to the interaction with the massive envelope, jet inevitably develops a lateral structure which shows a powerful fast-moving core at the center, and which is surrounded by a slower decaying wing-like region. And so when the observer line of sight is aligned within the core angle of the jet, spectral peak energy and luminosity is insensitive to the viewing angle. But as the viewing angle becomes larger and observers start to see this decaying wing region, spectral peak energy and luminosity declines rapidly with the viewing angle. And this decline at the wing region, decline of the 2 quantities in the wing region produces a correlation between the 2 quantities in all 3 models. So, and here is a comparison of the observed Amati and Ionotop relation with our simulation results. With here, with the plots with error bars showing the observation data and the color plots showing the simulation results. And as you can see, all 3 models shows a very good match with the observations. There seems to be some systematic shift towards a higher EISO in the Amati relation, but this can be simply interpreted as a result of the relatively long injection duration of the jet imposed in the simulation. Indeed, our simulation shows emission duration of 100 seconds in the rest frame, which is much larger than typical long-zero beats. So we expect that if we impose a shorter injection duration, it will provide a better match to the observation by reducing the ISO and the duration of the emission. But anyway, so the main message here is that although further confirmation is necessary, the photospheric emission can give rise to Amati and Yonetoku relation. And let me again briefly mention on the viewing angle dependence of the emission, which is a which plays a key role in reproducing the correlations. As I said, due to the interaction with a massive stellar envelope, jet develops a lateral structure which has a fast core in the center surrounded by slow decaying wing. And here I'm showing with dashed lines, sorry for the visit plots, but here I'm showing with the dashed line the kinetic energy distribution with an angle, and also the Lorentz factor distribution with an angle. And as you can see, beyond the core angle, both the energy and the velocity decline rapidly but continuously. So this continuous decay of the flow results in continuous decay in the spectral peak energy and luminosity, which is shown in this solid black and red lines. So as I said, this decaying feature beyond the core is playing a role in producing the correlations. For instance, if we consider a top hat-like jet, if the viewing angle is beyond the angle of the opening angle, the spectral peak energy and luminosity will drop so sharp that it will not lie on the correlations. So unfortunately, at this point, we don't have a clear theoretical interpretation on why the simulation results in a structure that will naturally reproduce the correlations, but this will be explored in the future. So, and we also did a time-resolved analysis in our simulation and find that the correlation between the spectral peak energy and luminosity holds not only among the bursts, but also within the burst, as inferred from the observation. So we think this is also providing a support for the photospheric emissions, emission mechanism of GRBs. Okay, so this is a slightly different topic, but in the Wednesday's session, Bing pointed out in his talk the importance of to check the correlations between peak energy and luminosity and with the bulk Lorentz factor of the flow of the jet. And they indicated on the possibility that the photospheric emission badly fails to reproduce the correlations. So unfortunately, he seems to be not here today, but so yesterday I have quickly looked into this aspect in our simulation, and the obtained results are shown in these right panels. Actually, the match seems to be not so bad. We find a very good match between the correlation between the LP and gamma, and an agreement within the dispersion for the correlation between spectral peak energy and gamma, but with some systematic shift. And probably reflecting this shift, we also find a certain offset from the fundamental plane relation among LP, EP, and gamma proposed by Liang et al. 2015. And as shown here. However, we should take into account several caveats on this result. So one is that we expect some uncertainty in the observed gamma values, since this is not a direct observable. And also regarding the gamma measured in the simulation, which we estimate from the value along the line of sight, since there is a sharp angular structure of the jet in the wing region, this may not really represent the gamma that is observed as a onset time of the afterglow in the pink region of the jet. So which shows a low peak, which shows a low peak energy and low luminosity, and where actually we find these offsets. So taking into account these uncertainties in mind, although more careful analysis is definitely required, I think that the current results does not have a serious conflict with the observed correlations. Okay, finally, let me move on to recent work on short GRBs. So here we also conduct a simulation in the context of short GRBs. Here we consider the jet that is launched from a black hole accretion torus system that mimics the system after the collapse of the binary neutron star merger. And the jet is ejected at the center, and its evolution is solved until it breaks out the merger components. So this is an animation of the simulations. Initially, we find a very strong interaction between the jet and the wind launched from the accretion torus. And after this initial interactions, the jet will eventually penetrate through the merger ejector components and breaks out and will propagate to large distance up to the point which it becomes optically into radiation. And so this is the result for the EPES and EPLP correlation in these simulations. As in the case of long GRB simulations, we also find correlation between these quantities also in this simulation. However, while the correlation slope shows a very good match with the observed one, we find a certain offset from the distribution of short GRBs in this case. Although it is not clear at this point, we are speculating that this offset can be reduced by changing the simulation setup within a reasonable range of parameters. And this will be tested in our future studies. Okay, so this is the summary of my talk. The main message here is that the correlation among spectral peak energy, luminosity, and the EISO can naturally arise as a result of the simulation of photospheric emissions. And EP and the decline of EP and LP beyond the core angle of the jet resulted in these correlations. We find that good agreement in the case of long GRB simulation, but some offset is seen in the short GRB simulation. So we are planning to further explore on this offset in future studies. We also explored the correlation between the bulk lens factor, and while does not provide a perfect match to the observation at this point, we think there is not this is not a serious conflict, taking into account several uncertainties that will play a role. So, but from conclusion, we need further careful analysis. So this will also be explored in the future studies. And that's all. Thank you for your attention.
Thank you very much for the last talk. Any questions?
I have a question. Ito-san, do you have the possibility to extend the photospheric emission? We have spoken about this several times, but what is the status for extending this until the plateau phase, for example? I know that it's very time consuming in terms of simulation, but can you comment a little bit on that?
Yeah, actually, we did such a simulation. Maybe you remember, but yeah. But we did with a very coarse resolution. Well, if we sacrifice the resolution, we can do a long simulation. And indeed, we did such a simulations. And yeah, we find that in some sense, plateau emission can at least qualitatively also explained by the photospheric component. But yeah, we didn't go into detail on that, so sorry. So I don't have a good answer to it now.
Because it would be nice to see also if the fundamental plane relation can be explained within the photosphere luminosity, peak luminosity, luminosity at the end of the plateau and time at the end of the plateau explained within the photospheric emission.
Yes, I agree with that. Yes, that would be interesting. Yes.
Okay, thanks. Any more questions?
I have one question. Hello, am I audible?
Hello? Yes, I can
Yes.
hear you.
In the simulations of short gamma ray burst that you showed in just last two, three slides, one of them, am I wrong when I say that the densities in the winds is too high? It's 10 to the 6, 10 to the 7 grams per cm cube. So will the
Sorry.
yeah, here. If I see
Sorry,
in
okay,
the first,
you're
in the first panel, you see the densities is 10 to the
okay.
7 8 grams per cm cube.
Okay. Okay. Maybe you are concerned about the density, which is higher than the ISM or something, or not? Do I follow your point?
In the first panel, when we see the log density plot, it's 10 to the 7 grams per cm cube in the winds in the later stage if you run this. So do winds have that much density? It's several,
yeah. Sorry, I don't have the exact number, but yeah, it's shown as here, I guess. So maybe at this point, wind components has say 10 to the 5, 4, or 6, yeah, here.
Do winds have that much densities?
Sorry, I could.
Yeah.
Sorry, I couldn't hear clearly.
Can we expect the winds to have that much densities around these objects?
Well, I would say it's not surprising because the assumed accretion torus mass is we assume kind of typical values. So, and the wind reflects the configuration of the torus. So I think it's not so surprising.
Okay.
Yeah. Yes.
Okay, thanks. Any more questions? Okay, if not, let's thanks the speaker, okay? Okay, let's keep going to the next speaker, the Dr. Conrad Warren. He will talk about consequence of a hotter thermal electron distribution in gamma ray burst afterglows. Okay.
Hi, I assume that you can all hear me and see my screen. Tell me if I'm wrong.
We can.
Thank you to the organizers for giving me the chance to speak. Thank you to you, the viewers, for getting up or staying up or just being up for these sessions, depending on what your local time is. So, as mentioned, I'm going to be discussing consequences of a hot thermal electron distribution in gamma ray burst afterglows. My name is Don Warren. I work in Japan. And if you take away one thing from this talk, please note that the red line and the black line are not the same. These are possible electron distributions with the same overall normalization and very different shapes. And this is work I've done in collaboration with these people and several others. So not published yet, waiting on someone to finish organizing a meeting to get comments on this paper.
Sorry, apologies.
You've been busy. As a very quick background, I guess if you've made it this far and you don't know what a GRB is yet, shame on you. So one slide on afterglows, that after the GRB, you have a multi-wavelength relic, everything from radio to now TeV gamma rays. And so these afterglows are observed from 10 to the 9 hertz out to 10 to the 25 and beyond now, starting minutes after the trigger to months and occasionally even years after the burst. And I love pushing this paper because of how optimistic the title is. You've got many different models that people have used to explain this breadth of energy and time data. And so you've got this 50-page paper, 20-something figures, 40-some 20 tables, 40 figures, hundreds of equations. This really optimistic title that, as far as I can tell, is true. And they've got pretty much everything in there. But despite the success of the analytical synchrotron external shock model at explaining so many of these features, it's not without problems. So sometimes there are issues, like in this paper from Dale Frail, where half the GRB energy is in electrons, half of it is in magnetic fields. Or this later paper by Tamoy Lashkar, where again, roughly 100% of the available energy is in electrons or magnetic fields, which is a problem because there are also ions present that need to have some non-zero amount of energy, and in all probability more than the electrons. This was stated even more well, brutally, I suppose, by Thomas Kangas and Andy Fruchter earlier this year. We show that most of the events in our SWIFT sample are incompatible with the radio light curve behavior predicted by conventional afterglow theory. Okay, so that's an outright claim of incompatibility. So what's going on? Well, problem is that GRB forward shocks look very different at large scales and small scales. At large scales, you just got this blast wave pushing into the ambient medium. And at smaller scales, you have magnetic field turbulence produced by relativistic instabilities, and they cause magnetic fields to grow towards the shock and decay away from the shock. And as the electrons and ions travel towards the shock, the ions lose energy, the electrons gain the energy. And so what you wind up with is a robust prediction that electrons and ions should have almost the same energy as they cross the shock. It's not just Lorenzo Ceroni's simulations. Kazem Ardana has seen this. It's been seen in other PIC simulations, predicted analytically by Mikhail Medvedev, Martin Lemoine, and Guy Pelletier. Yeah, and again, stated explicitly, equipartition with the incoming ions for the electrons. So these electrons are going to be hot, and they're not going to take the shape of a pure power law. There we go, blinking for extra emphasis. What they are going to have is a thermal-like, and maybe not exactly Maxwellian, but thermal-like distribution that sits right at the base of the accelerated power law tail. So assuming that these various people I just cited know what they're talking about, this is going to be the case. So what do we do with this information? Well, the goal in this paper, which is going to be submitted soon, hopefully, is to create a semi-analytical afterglow, including these thermal electrons. So step one, create an electron distribution with both thermal and non-thermal particles present. Choose a power law, choose a fraction of electrons in that power law, because you could imagine more or fewer electrons being injected into the acceleration process. Step two, place this distribution inside a model for a shocked GRB jet. Now, this is the egg from Granat et al. 1999, where everything in this region can emit photons that arrive at Earth at some particular observer time. So the actual blast wave is assumed to be spherical in a lot of these treatments, and ours as well. So you have some GRB parameters, kinetic energy, ambient density, equipartition fractions, this participation fraction FNT. So we're saying roughly 2% of the electrons come out of this thermal distribution and are accelerated into the power law tail. And that was chosen specifically so that it would match up with an equally normalized pure power law. There's no physical reason to choose this 2% value and place it at some cosmological distance. And then once you've done that, you need to solve the radiative transfer equations, integrate along the lines of sight through this shocked region, and total up all the intensity. So you can get computers to do that for you. And one of the big things that we're doing differently here compared to previous work is including synchrotron self-Compton, which as far as I know hasn't been discussed in the context of thermal electrons. So here are some consequences of these different distributions. So the thermal electrons are responsible for a noticeable peak in the synchrotron compared to, black is for a thermal plus power law distribution, red is for a pure power law. So a significant peak in synchrotron, and then a larger enhancement due to thermal synchrotron self-Compton. So this enhancement in TeV energies lasts for the randomly chosen parameters. So plausible, but we were not attempting to fit any particular burst. This enhancement can last for hours after the trigger. And it can be an order of magnitude or even more enhancement with thermal particles compared to without thermal particles in this TeV range. And then you also have some oddness going on at radio, which can potentially explain the inconsistency between predictions of the standard synchrotron afterglow and observations. So these low energy light curves, optical and radio, they peak later if you have a thermal distribution, because the peak of the thermal distribution is at higher energies than the minimum injection energy for a pure power law. So it takes longer for the characteristic synchrotron frequency to get to whichever waveband you're observing in. So that's a factor of 5-ish delay in peak optical, and it would be similar in radio, but we can't simulate that long because the Blandford-McKee solution ceases to apply after a particular observer time. At higher energies, X-ray, GeV, TeV, the light curves are enhanced. This is due to the thermal synchrotrons or the synchrotron self-Compton radiation. And then as the thermal peak passes out of whatever waveband, the emission you see is produced by the power law, and so the power law and thermal plus power law light curves agree. Now, I think someone mentioned in the first day the strange agreement between X-ray and TeV for one of the more recent bursts observed at that energy range. And again, we did not choose the GRB parameters, but what we get is a natural agreement in enhancement between X-ray and TeV that peaks at about the same time and decays at about the same time. So this just fell out very nicely without any additional effort on our part. If you look at the spectral behavior, look at the light curve behavior, you can express this as traditionally done. F nu proportional T to the minus alpha, nu to the minus beta, where these come from either the light curve or the SEDs. Now, restricting this just to X-rays. The blue line here is the expected behavior of the standard synchrotron afterglow. The red curve is what you get if you applied my semi-analytic code to a pure power law. This difference is numerical in nature. I think I might be able to get rid of it, but either way, it can be post-processed out because it's systematic. But you can't post-process this out. This meandering path taken by the black curve through this alpha beta space is due to the presence of the thermal electrons and the peak they produce in the synchrotron radiation. So I want to point out that the afterglow is slow cooling. You can plug in the energy, the ambient density, the epsilon E, epsilon B into the standard afterglow formula, and you get that the transition time between fast and slow cooling is something like 6 seconds in the observer frame. That's earlier than any of the points here. So 10 seconds, 100 seconds, 1,000 seconds. So the afterglow should be slow cooling everywhere. But that's not the behavior that the thermal electrons show. And if you want to relax the assumptions even further, So I mentioned that FNT, 2% of the electrons were placed into the accelerated tail. If you reduce that further, from 2% to 1%, 0.1%, 10 to the minus 4, then this meandering path through the alpha beta space gets even more extreme. And so even though we know that this is an afterglow expanding into a constant density medium with a power law index P greater than 2, and it should be slow cooling, these paths escape those closure relations completely. So this region is for slow cooling, this region is for fast cooling, and this is just not predicted at all for this physical scenario. But what is interesting is the late time behavior. So after 10 to the 3 seconds, 10 to the 4 seconds, depending on the value of FNT. These dots are 10 to the 3 seconds in the observer frame. These are 10 to the 4 seconds. You get something that looks kind of like what Judy Rakison compiled back in 2009. So for afterglows in phase 3, the standard decay phase, not plateau, not jet break, just the traditional afterglow. What she found was that alpha is clustered around 1.2 with this tail towards higher values, and beta is clustered around 1.1, 1.2. And if you squint, maybe you can convince yourself that's asymmetric. I won't stake my career on that. But this is kind of what you see for low values of FNT when you have thermal electrons. You have, at late times, beta clustered around 1, 1.2, and alpha could be much, much greater than that. So I'm going to steal a trick from, I think it was Asaf when he gave his talk, and match question mark. So this is not conclusive, but it is suggestive. Again, this was with no particular effort on our part. All we did was assume that these electrons had a thermal distribution that was joined to the base of the power law tail. So there's more in the paper that will be published eventually, I sincerely hope. But for now, I'll wrap up that thermal electrons are robustly predicted by both analytical theory and numerical simulation. The thermal distribution is very different from a pure power law distribution at low electron energies. Instead of rising at the same spectral index, you get a thermal peak and then the decay, and you have a bunch of electrons down here below where the pure power law ends. And this different electron distribution results in different SEDs. And you can look at the ratios here and see the enhancement at synchrotron, from the synchrotron thermal peak, and even more enhancement from thermal synchrotron self-Compton that lasts for hours. It can last for hours, even for the pedestrian GRB parameters that we assumed. And the X-ray closure relations that so many people love to mess with and use to interpret afterglows, those get modified also. And the modifications can be extreme if injection is not efficient, if a small fraction of electrons find themselves pulled out of the thermal distribution and accelerated into the power law tail. And that's all I wanted to say today. Thank you for your attention. And I guess I have time for questions.
Thanks very much for your nice talks. Questions?
I have a question. So thanks, Don. Very nice talk. So I very much agree with your sentiment that synchrotron self-Compton is unavoidable when looking at afterglows. This is true even without the non-thermal, even without the thermal distribution of the electrons.
Yeah.
So the fact that there is, as you've shown in your introduction, many bursts which seem to be in contradiction with standard afterglow fitting. If I take devil's advocate here, this could simply be because they're using synchrotron models as opposed to models that also include synchrotron self-compton cooling, which again is something that is unavoidable. So it would be nice to compare your results with the thermal fraction to cases where you look without the thermal fraction but still include the SSE.
Okay, so these 3 papers here were all radio papers, so not a TV photon to be mentioned here. And
yeah,
I didn't
but when I talk about
talk.
SSE, I mean actually not for the SSE emission, but for the SSE
Yes.
cooling.
Yes, so I didn't put this in the talk, but it's in the paper. So if you wind up refereeing it, you'll get advance notice. The Compton parameter Y is significantly lower than unity at all times for these parameters that we picked. So we can look at the luminosity ratio, and Y is 0.1 or less at all times. So it shouldn't make a big difference on cooling.
Yeah, I'm not saying it should make a difference for the parameters you've chosen. Of course, the values for those parameters where Y would be small. I'm just saying that when we compare the other models, for them, we don't know what the result would be for the areas in the parameter space for which Y could have been large, because they simply don't account for those cases consistently.
Okay.
Okay, thanks for the questions. Any more questions? Okay, if not, let's thank the speaker again. Okay, and then let's move to the next speak, the Dr. Sam Altus.
No, there is first Nissim, Freya, Liliang, and later Sam.
Okay, sorry.
Okay, thanks, Maria. Thanks, Lion. I'm going to share my screen.
Okay. He will talk on model flash breaks and energetic photos in gamma ray burst, Fermi light crest. Okay.
Okay, a full screen mode. 1 second. Okay, can you see my screen?
Yes.
Okay, perfect. Good morning, good afternoon, and good evening to everyone. Depends on the place you are. It's a pleasure to be here. Thanks for the invitation today. I'm going to talk about the modeling flares. 1 second. Breaks and energetic photons in gamma ray bursts, Fermi light curve. I like to begin by saying about the motivation. Fermi team presented the second Fermi light GRB catalog covering the first 10 years of operation from 2008 to 2018. The catalog comprises 169 GRBs with higher emission larger than 100 MeV, 29 bursts with high energy emission larger than 10 GeVs. That's 60 GRBs with temporary extended emission, but half of them presenting a GeV peak in coincidence with the prompt phase, most of them at the end of the prompt episode. Just 21 bursts show a break between 63 and 1,000 seconds. And although the long-lasting emission is usually interpreted as synchrotron radiation from external forward shocks, not all light curves satisfy the closure relation, as expected in the afterglow forward shock model. You can see some example of the light curve. Okay, to interpret GeV flares in the light curve, we derive the synchrotron self-compton light curve from the reverse shock, and in addition, we investigate the break exhibited at 100 seconds using the synchrotron forward shock model. So, first of all, we're going to describe the theoretical model, the synchrotron self-compton light curve from the reverse shock emission. So, a reverse shock propagating into the GRB jet is produced when a relativistic ejecta interacts, everyone knows, with the external medium, so that the dynamics of the reverse shock can be described through the evolution of the Bohr-Lorentz factor during the acceleration phase that depends on the set of length and the shell's width. And K is the power law index of the density profile, is the kinetic equivalent energy, is the parameter density, and every one of the constants, speed of light and the proton mass. Also is very relevant to define the critical Lorentz factor. Yes, that is the comparison with the duration of the burst. So taking into account the duration of the burst, it is possible to define two regimes. The thick and thin, 1 second, I'm going to pass to the other side. The thin and the thin shear regime, okay? And the thick shear regime, the reverse shock becomes ultra relativistic and therefore can decelerate the shell substantially. In the case, the shock crossing time, Tx, is less than the duration of the burst. So to derive the light curves for a thick shell regime, we describe the dynamical before and after the shock crossing time. But if we want to derive the light curve, it's necessary to derive the evolution of the magnetic field, the electron factor, the synchrotron spectral breaks in the reverse shock region. So it's not easy when you do for a general case, power law index and density profile. So I avoid to include this equation here. I just put the synchrotron light curve in that case. So in that case, for general K is, as you can see, and for the thin shell regime, in the thin shell regime, we need that the reverse shock is mirror relativistic, and the T90, the duration of the burst, is less than the shock crossing time. So we the same evolution, dynamics, and all what we need to derive the spectral and synchrotron and synchrotron self-content spectral breaks, and you can derive the synchrotron self-content light curve from the thin shell regime. So it's very complicated. Now, hereafter, we're going to show just for the homogeneous density medium or the constant medium. So it's easier in that case. Again, the left-hand column is for before crossing time, and the right column is for after crossing time. In both cases, you can see the closure relation for the thick and for the thin regime. So, okay, important here is the synchrotron light curve, yes, that you can compare with the standard forward shock emission and other kind of model with an injection, something like that. Okay, in that cartoon is the theoretically predicted synchrotron self-content light curve from the reverse shock is in blue line. In red line is the synchrotron light curve. Everyone knows the evolution of the forward shock, the synchrotron spectral breaks evolution, the characteristic, the cooling frequencies, the maximum flux, depending on the time, for example. This is in red lines. So in both cases, we put in the fast and slow cooling regime. So predicted light curves are presented in the thick and in the thin shell. In the thick is the left column, and in the thin is the right column. Both are for uniform density medium for ICM. So light curve from both to bottom is in the fast cooling and slow cooling regime. So gray dashes is associated with the shock crossing time. Blue dash line indicate an alternative power law evolution of the synchrotron self-control model. So here you can see that closure relation for a superposition of both synchrotron self-control and synchrotron, both from reverse and forward emission, are not satisfied. That what happened and were reported by the LAT team. So you can see here that in the thick shell case, the temporal rise index and the temporal decay index is in this range, is atypical, and in the differential case also the same. For instance, when you consider a spectral electron index, Paolo index, yes, in this range and appears in the here in this part, the temporal rise and the temporal decay indices are as appear in that. So, okay, here is the parameter spaces, yes, for the synchrotron self-contour light curve and from the reverse shock and synchrotron light curve from the forward shock. So upper panel range the microphysical parameters and density for which synchrotron self-contour emission, excuse me, is above 5 times -5 millijansky. That is close to the last sensitivity for a kinetic energy, kinetic equivalent energy 10 to 52, the left, and 10 to 54 is right. So the lower panel range the microphysical parameters of the density for which the forward shock synchrotron emission exhibits a break, a temporal break between 100 and 500 seconds to the passage, the cooling frequency. So we have to we take two assumptions. The synchrotron self-contour from the reverse shock emission is in the thick shell regime at 10 seconds during the front phase, usually in the long gamma ray burst. And the second assumption is the forward shock cooling frequency causes the 100 MeV, the lat energy range between 100 and 500 seconds. So the most important or the relevant characteristic of the conclusions here is that the parameter, the only parameter that satisfy both conditions, that the bright lat peak and the break, the temporal break between 100 and 500 seconds, is when the epsilon E at the reverse and the forward shock are equal, but the epsilon B, the microphysical parameter given to amplify or create the magnetic field, is larger in the reverse shock from the forward shock. Yes, with the very low density. In this case, it's 10 to -3. That is relevant that, and this is our conclusions. Now we're going to apply, we're going to model just one gamma ray burst, the GRB 160509A. Of course, we are going to apply to stratify medium with different Paolo index of density profile, but for this example, use just K equals Z, constant medium, density constant medium. So this is the light curve of the 160509A. LAT detected this gamma ray burst, and GBM and LAT triggered this gamma ray burst. This burst presented two components. The first component is associated with the GB flare that begins, that with a duration of 20 seconds, and an extended emission that begins at 40 seconds and extends for more than 1,000 seconds. So we fit both components, the GB flare and the extended emission, as you can see here, using two broken power laws. And of course, in that case, we obtain the best fit parameters, which is the GB flare and the standard emission, the temporal spectral index, of course, in both cases. So, and Tanetal in 2017 obtained reported the spectral index before 300 seconds. Here you can see the temporal index at 300 seconds. So it's separated in two time intervals, one in the panel and two. So we apply the closure relations, and the LAT observation satisfy the the closure relation, and synchrotron self-compton from the reverse shock. And the synchrotron forward shock, in both cases, you can see the electron spectral index are not equal, but similar. And the LAT, the frequency at the LAT, the frequency at the LAT and the LAT range is between the characteristic and the cooling frequency before 300 seconds, and after a move is larger than the cooling and the characteristic frequency. It's worth noting, it's relevant to say that two very high energy photons were detected. The first one reported an arrival time at 76 seconds with an energy photon of 52 GeVs, and the next one was detected at 242 seconds with an energy photon of 41 GeVs. It's very important here. Next, okay, to constrain the LAT light curve and spectrum, we need to constrain the parameter or to model the afterglow observations. This gamma ray burst 1605098 was detected in X-ray, optical, and radio band. The left-hand panel, you see the optical and X-ray bands, and on the right-hand panel, you see the radio and several wavelengths. So you see here that the optical emission is eclipsed, hidden by the host galaxies. The host galaxies dominate the flow, so we cannot work with the optical emission. And the radio wavelengths are observed in a time scale of days. So we need to constrain the parameters during the early afterglow. So we are only work with the X-ray observation, XRT observation. Okay, this is the XRT light curve. Okay, we divided in three intervals. We fit using a simple power loss and obtain the best fit parameters, the second, 3, and 4 regions, and the time interval, and this is the temporal and spectral index. You see that, well, you can see the standard synchrotron forward shock model. You see that what is the plateau associated with the plateau, followed by the normal decay, and the last associated with the jet break. Again, what we can do is to calculate, to obtain the closure relations. The first one is using the standard synchrotron forward shock model. Okay, and the XRT observations satisfies the closure relation with P electron spectral index 2.3, similar to the previous one, but the frequency at the XRT energy range is larger than the cooling frequency. Yes, and for a time larger than 50,000 seconds as the conditions. So we have a problem here. We have two breaks. One at 100 MeV, yes, in the Fermi LAT observation. The second one is at XRT energy range, yes, one at 300 seconds and the other at 50,000 seconds. So well, it's a problem because it implies a rapid evolution. But this is, everyone knows here that the cooling spectral break evolved at T2-1/2 is slow. Actually, it's very slow. So the problem is to look for a mechanism that we can describe this rapid evolution. But this similar rapid evolution of the cooling spectral break has been inferred in other cases with potential explanations involving time evolution of the microphysical parameters, steep circumburst density profiles, energy injection into the forward shock, and the proximity of the jet break. So now, in our case, for this burst, we are going to consider the evolution of microphysical parameters. Here, you see here that epsilon E evolves as time and epsilon b evolves as time, as you see here. The synchrotron spectral breaks evolves as this, the characteristic and the cooling frequency spectral breaks evolves as you can see, and the synchrotron light curves, in that case, with the evolution of microphysical parameters, becomes as this equation. You can see here, of course, it's trivial that with gamma E and gamma B equals 0, the standard synchrotron forward shock model is recovered. So, in summary, we have to describe the Plateau phase, and we need to describe the evolution, the rapid evolution from the cooling frequency from the lat energy range to XRT energy range, and with this spectral ordering, okay, in these intervals. It's not easy, but what we see, the first was this is what going to fit the analytic with our model, the analytic afterglow model, constant homogeneous constant model, that is determined by 9 parameters, with a prior distribution for application in the Monte Carlo Markov-Chain simulation and CMC simulation, where we normalize the synchrotron forward shock and synchrotron from forward shock and synchrotron of content for reverse shock models at 100 MeV to describe, to explain the lat observations, and synchrotron forward shock model in the standard and the lateral expansion after the jet break, okay, at 1 kV, in order to describe the XRT observation. Okay, the evolution of microphysical parameters is included, and the luminosity distance is obtained using the cosmological parameter reported in the Planck collaboration. So this is the multi-wavelength light curve of GRB 1605.9A with uncertainties, with the lat, and with the XRT using the synchrotron of Compton reverse shock model and synchrotron forward shock model. So, and this is the current plot of the parameters, and this is the median value of the parameters. This is the best fit values. So now with this value, we're going to explain and implication and results. Of course, we're going to discuss with the value. The first one, the microphysical parameter. So, given the microphysical parameter associated with the magnetic field in the reverse shock region, epsilon B R, we can obtain the magnetic parameter. There is the magnetization parameter, and the magnetization parameter you see in the plot, epsilon B F and epsilon B R, as a function of this parameter, magnetization parameter, is in this range, 0.04 and 0.2. This is very relevant. Why? Because if this burst could have been highly magnetized, so when this parameter is much larger than 1, or weak magnetized with the magnetization parameter much less than 1, of course the reverse shock would have been suppressed. But in our case, with an intermediate magnetization is needed, 0.1 to 1, to obtain the observed bright emission that is for our case. So in our case, we can explain the lat bright peak.
Sorry, 1 minute, okay?
Okay, perfect. Thank you. And okay, let me see, and you see that the reverse shock, the epsilon B, the reverse shock and the forward shock are different. So the evolution of microphysical parameters, here is the best fit values, and you see that when the magnetic parameter increases with time, the electron density parameter decreases, and this is the evolution of the break evolves, and this one, and synchrotron flow evolves, as you can see here. You see that the temporal index matches or is consistent with the Plateau phase. So the rapid evolution of the cooling frequency indicates that the breaks observed in the lat and XRT light curves at 300 seconds and 50,000 seconds can be interpreted as the passage of the synchrotron cooling break through the Fermi-Lat and Swift bands at 100 MeV and 1 keV. So I think this is the last one, no, two more or less. Okay, the very high photon about synchrotron limit. So with the best parameters, we plot the maximum energy of the synchrotron photons as a function of time, and you can see that the synchrotron limit is far below from the two very high energy photons. So a synchrotron process cannot describe these photons. We need a new mechanism that evolved with the during the forward shock, and the most appropriate, the suitable mechanism is synchrotron of quantum emission. We obtain the synchrotron of quantum spectral breaks and maximum flux as a convention. We obtain the spectrum, and in that case, with the best fit parameter, evolved with the second power law. In this power law, with this flux, what we did this was to obtain the number of very high energy photons, and you can see here the number of photons is 1. Yes, matching with the replacing with the flows, replacing with the time, replacing with the area of Lat and the energy. So this result is in accordance with the model that we applied to describe the GRB, reproduced the two photons observed for this gamma burst. So the declination is far away. So other characteristics, you can see that the best fit value of the circumference density is very low, and it's comparable to a halo intergalactic medium. As you remember in the previous, the first part of my talk, the fair lower density agree with our prediction. We can describe at the same time the Lat light curve, the bright peak light curve, and the break observed during the long-lasting emission, just if the outflow is magnetized and evolves in a very low density. So the initial Bolognese factor is typically in the range that reported by Fermi-Lat. Yes, and the conclusions, we are running out of time. This is the first one, derive the synchrotron self-contour in the thick and the thin shell regimes for a stratified medium, but just I showed you for K0, the power law index for density profile with constant density, homogeneous density. Okay, we can describe the GB flares. The second one investigated the nature of the late time breaks, GB. You remember that more than 50 gamma bursts presented in the Lat, the second Lat catalog presented this break, and this break is interpreted the passage of the synchrotron cooling frequency of the forward shock through the GB band. This naturally occurs in a uniform low density environment. And the last conclusion, we applied the model in the thick shell regime in this gamma bursts. We can describe the two very high energy photons produced during the acceleration phase, and we apply the synchrotron self-contour from the forward shock emission. So a magnetized outflow could explain this feature. And the last one is the variation of microphysical parameters described in Plateau phase. As you can see, and the breaks observed in the Lat and the XRT like of 100 MeV and 1 keV. Yes, at the passage of the synchrotron cooling break. Thank you, everyone. That's all that I have to say. Thanks for your attention. Questions, comments? Okay, perfect.
Okay, thank you very much for the nice talk. Sorry, we are running out of the time. We would let the last speak. Some authors will talk exploring the behavior of the non-gamma bursts with the intrinsic afterglow correlations. Okay.
Yeah. Just bring my screen up.
Yes.
Can you all see that?
Yes.
Okay, great. Okay, so good morning, and thank you for paying attention till this last talk. So I'm going to talk to you about a correlation that we've observed in the gamma ray burst afterglow light curves. It's a correlation that between the brightness of gamma ray burst afterglows, their intrinsic brightness, and the rate at which they decay. And this is something that we've observed in both the optical and the X-ray light curves. And this is work that I've done, and also Judy Rakusin has done quite a bit of work on this. So I've given you the main conclusion already, so let's just jump in and show how we got to this point and what it means. So here's the sample of X-ray and optical light curves. Opticals on the left, X-rays on the right. And you can see that they both cluster and that the distribution in luminosity appears to be wider at early times compared to late times. The X-ray light curves are color-coded by luminosity, so the brightest are red, faintest are purple. And you can get an indication here that the brighter ones seem to have steeper slopes. So we wanted to try and quantify this. So we measured a luminosity at rest frame 200 seconds, and we took a very basic parameter of the average decay rate from 200 seconds. So basically we just fit a power law to the data, and we didn't care about the underlying behavior at all. So we're just taking something fairly simple. So if you take those two parameters and plot them, you end up with these two figures. Optical gains on the left, X-rays on the right. Apologies, Judy did the inverse of the temporal slope, so they look like they go in opposite directions, but they are both doing the same thing. And in both figures, we get a fairly reasonable correlation. The X-ray looks slightly weaker, but I'll show you a few more slides where we tighten this up a little bit in a second. What's interesting to note is that the slopes of both correlations are consistent. So as we know, the X-ray light curves are quite complex in their behavior. On the right here, we've got the canonical X-ray light curve. So this is in comparison to the optical. The optical is a bit more simple in behavior with one or a couple of power laws in general. The X-ray is composed of up to 5 segments, and it might have some prompt emission contamination from the first steep decay segment, and also the flares. And also we quite prominently see the shallow decay phase in the X-ray light curves, where it's not as clear in the optical. And we wanted to see if any of these features introduced a lot of the scatter that we see in the X-ray correlation compared to the optical. So the X-ray correlations on the left, you see above the dotted line, there's quite a few scattered points here. In addition to those effects, we also wanted to have a look at short versus long gamma ray bursts. So in the X-ray sample, we have both, whereas the optical sample, we just had the long gamma ray bursts. So let's take a look. So what do I mean? How can the prompt emission affect the parameters that we're measuring? So the initial steep decay. So the figure on the left, both figures showed the light curves with steep decay. The figure on the left shows that the steep decay ends before 200 seconds, and this isn't a problem for parameters. So if you measure from 200 seconds the average power law decay rate, and you measure the luminosity at 200 seconds, you get fairly reasonable approximations for the behavior of the afterglow. The figure on the right shows this is a problem for the rest frame 200 seconds. You have quite strong contribution from the the tail of the prompt emission at this point. If you just fit from 200 seconds onwards a power law, you get the pink line, which is quite steep and dominated by the tail of the prompt emission data. So for this case, we ignore everything after the end of the prompt emission, and for the average power law, we just fit data from this second dotted line onwards. To get a better estimate of the luminosity, we extrapolate from the green line the point at the dotted line. So we extrapolate that back to get a better representation of the luminosity. So just before I apply this correction, let's have a look to see which bursts have this problem. So the figure on the left shows this. We highlight in black those points that have the tail of the prompt emission contaminating the light curves at rest frame 200 seconds. And you can see that's a lot of the points that are scattered in this correlation. And if you run the correlation on just those points, you don't get you don't get a consistent correlation, at least. You get something quite different going on there. So from this point onwards, any future figures that you see, we are using the corrected values. So of the figures you just saw, getting a better estimates of the afterglow behavior. The figure on the right shows you short versus long gamma ray bursts. So we try and run the correlation on the two samples distinctly, and the long gamma ray bursts clearly show this correlation, but the short ones don't seem to have a correlation at all. But there are very few bursts in the short sample. So perhaps it's just we don't have a large enough sample to tell this yet, but it's not really giving us any strong indication that there's a correlation in the short sample. So we'll discard the short GRBs. Having a look at bursts with flares, so not doing anything about the flares, just separating the two sets of bursts into those with flares and those without. We rerun the correlation and we find that the a Spearman rank gives and the linear regression give consistent results between the GRBs with and without flares. So it seems it doesn't matter if the GRBs have flares or not, we still get a correlation. However, the flares are likely internal shock, so we have at this point refit all the bursts, excluding data which we can attribute to the flares, and we redetermine the parameters. This figure on the right shows the difference, separates the bursts into groups with and without plateau phase. And what's quite interesting is that you get correlation, you get a consistent correlation in both samples. So it doesn't matter if these bursts have a plateau phase or not, you still get a correlation. So after applying all these corrections and just checking the sample, we end up with these two final plots. And you can see the Spearman rank value of the X-ray sample has increased to be more in line with what we observed in the optical. And also a lot of the scattered points have disappeared from that. So what else have we done? We've had a look at those four parameters and compared them against the gamma ray properties. So the luminosities versus isotropic energy is given in the top plots, and the slopes versus the isotropic energy is given in the bottom plots. We also did this for e-peak, but I haven't shown the figures. The correlations in both sets are there, but it's slightly weaker in the e-peak ones. And what's interesting is that we expect correlation between the luminosity and isotropic energy, but we don't necessarily do with the temporal slope, the rate of decay, and the isotropic energy, but which we are seeing here. So what's the general implications of this? So it's showing us that the most energetic gamma ray bursts, so most energetic in the gamma ray emission, have the brightest X-ray and optical afterglows, and they decay more quickly than the less energetic ones. It's potentially suggesting there's a difference between long and short GRBs, because we're only seeing it in the long GRB sample, although I'd like to extend the sample a bit more for the short GRBs before we conclude that. But at least there's probably some difference. And the correlation in both bands suggests there's some single mechanism that's producing what we're observing, regardless of the detailed behavior of the light curves. And immediately we can exclude any mechanism that's producing this in just one band, for instance, the reverse shock. So what are some possible explanations? well, we had a look at the basic afterglow model, so where we assume a simple outflow, forward shock, no energy injection. And in this case, because you get a correlation between luminosity and alpha due to the closure relations, you should also expect a correlation between luminosity and beta. That's shown in the figure, top right figure here. The GRBs are color-coded by luminosity. So you can see a clear trend in luminosity with alpha, but you can't see it the other direction horizontally. And also we had a look at, because the closure relation, there's more than one to describe different spectral regimes. We ran a Monte Carlo simulation to see what you should expect typically for gamma ray bursts. While we could reproduce some of the observed correlations, we can't observe correlations that involve the temporal slope. So between luminosity and alpha and isotropic energy and alpha. So it leads us to look at more complex models. So perhaps the standard afterglow model is okay, but we need something, some extra mechanism or parameter that's regulating the energy release somehow, so that the brightest events release their energy more quickly and decay more quickly. Or perhaps it could be a geometric effect. So the figure, bottom right figure shows this. So different lines represent different viewing angles, and that those bursts more on axis decay steeper and are brighter. So perhaps it's just as simple as that. And just to add that we're running some simulations of this with Jeffrey Ryan. He's using his off-axis synthetic light curves to try and reproduce the correlations that we observe in the optical and the X-ray. And from a very quick simulation, this is just something we've started on, he is able to reproduce the correlation that we observe between the isotropic energy and the slope in the optical and the X-ray. And most interestingly, he gets slopes just from a very simple simulation that are consistent between the two samples. So it's really suggesting that this correlation can be simply reproduced just by varying the observer angle. Just one extra thing that we're doing right now to investigate this a bit further is to try and have a look at the GeV and the radio light curves. I've had a couple of master's students looking into this. The GeV is not very promising, but the light curves tend to be much shorter duration. So perhaps we just need light curves that extend over 10 to the 5 seconds to observe this. But the radio is much more promising. It's harder to get a good sample since they're observed over lots of different frequencies. But we've managed to collate just a small sample so far of 10 radio afterglows with redshift in the same frequency band. And from this, we're clearly detecting a correlation between the two parameters, the luminosity and the decay rate. At the moment, it seems to be stronger than what we're observing in the X-ray and the optical. So this is something we need to investigate a little bit further. So I guess I will just leave you with my conclusions, since you're probably all very exhausted from all the talks, and I'm open to any questions. And thank you for having me speak today.
Thanks so much. Thanks so much for your nice talk. So any questions? Okay.
There is a comment from Bruce that says that similar results were obtained with Beppo-Sachs, Bohr and Gendre 2000, Covelliotto et al. 2004, and Gendre and Bohr 2004.
Yeah, we do discuss this in our 2015 paper. If I remember, the Gendre paper does it over a later time window than us, and they observe a correlation that's in the opposite direction.
I think we discussed with you several times the possibility how this correlation that you see in optical and in X-ray, it is related with the luminosity time that I've found in X-ray and optical. We still didn't come up with a clear idea yet, but
yeah, I think that's something that's worth looking into further. I think it's interesting that this correlation that we're observing is it doesn't matter if you're observing the plateau phase or not. So it applies to all gamma ray bursts.
Yeah, that's true.
Yeah, so yeah, it's certainly worth looking into how you can get both correlations.
So you were mentioning, I have another quick question. You were mentioning that you are planning to extend the sample. What it is the number of GRBs for which we have extended in optical, or that you are planning to?
Yeah, I think it's at last count I had roughly 200. It's just waiting on me to finalize obtaining the host extinction corrections. I'm probably being very pedantic on this and running expect to get all the host extinction values, so it takes a little bit of time to do this properly. So apart from that and other projects that get in the way, that's all it's waiting on. So there should be about 200 or 250, I think, in the optical.
Okay, thank you.
Okay. Other questions?
I have a question. Hi, Sam. It's a very nice presentation. I would like to ask, when you see like a second peak in the butt light curve, very bright, or flares, how does it affect afterglow slope, for example, after the plateau?
Well, I guess that's not something that I've looked into actually specifically. I don't know if anybody else has thoughts on that would know.
Actually, I feel that it's more steeper. I just wanted to confirm if you.
Yeah, well, at least this correlation is showing that afterglows that are more steeper tend to have brighter, or more energetic prompt emission. So I guess if has huge flares in it, then potentially it's going to be more steeper, more luminous.
Okay, yeah, thank you.
Okay.
Can I ask a question?
Yes, sure.
Yeah, so thank you for the nice talk. I'm interested in the slide you show about the simulation by Geoff Ryan. So could you explain a bit more about their setups? So do you assume some kind of structured jet for the simulation, or could you explain more about it?
Yes, I don't remember right now. I think
okay.
you have to go back to his 2015 paper and look at the details.
I see, but did you get the result by kind of tuning the parameters, or it's?
I don't think he's tuned anything. The only thing he looked at was just changing the observer angle.
Okay,
thank you very much.
Okay, thanks for all the questions. Any more questions? Okay, if not, let's thank all the speakers today. Maria, can you give some comments on the summaries of all these three?
Yes, I would like to thank all the speakers, not only of today's session, but also on Wednesday and Tuesday session. And I would like to also say that it has been very interesting to see that we have learned how the several classes of GRBs, they follow or not some correlations, how important it is the correction for selection effects in short GRBs, and how the magnetar can fulfill majority of the cases with the plateau emission, but it is not the only model that can work. Diversity of supernova, we learned also of the joint mission and new mission. So I again want to thank you all, because this 3 session, I think, clarified more some of the critical points in GRB correlation, the observational challenges and theoretical implication. So thank you all again.
Thank you. Okay. Okay, bye-bye.